This is Dr. Lata, heading Computer Science and Engineering Department in AIMS Engineering College, situated in Banerghatta Road, Bangalore. The college started in 1999. Currently, we are running 9 UT programs and 5 PG programs. It's headed by our beloved principal, Dr. H. Natraj. And it has a very vast history of good academic record with 30 VTU ranks as of now, and with a sprawling campus of 52 acres. And now I'm heading Computer Science and Engineering Department. In Computer Science and Engineering Department, we have an intake of 240 currently and one PG program, Computer Science and Engineering. Again, in the department, we have a history of 12 VTU ranks and very good academic record of 50 faculty members, among which around 10 are doctorates. And very recently, we conducted a crash course for all the critical subjects of fifth semester and third semester, like finite automata for fifth semester and data structure for third semester, and so on. So, with the overwhelming response of all those crash courses from your heads, faculty, and your fellow students, there were so many inquiries to conduct the same for this computer organization. Initially, we were very apprehensive because computer organization is a very vast subject that cannot be covered as a crash course. But then we thought we'll deal with only the critical points of that particular computer organization subject and we'll take it up for 3 days. And when I inquired, our faculty, Indu Jain, Professor Indu Jain and Professor Salangai Naigi and Professor Veena Bhatt came forward to take up this consignment. And they all are very experienced and have taught the subject for quite a number of times. So they are the right persons to take up this course, and you all can feel free to get your doubts cleared and follow it up with the phase with those crash courses. And if you have any doubts, get it cleared then and there and try to score good marks, because computer organization is the basic subject for a computer science engineer. You'll have to know all the concepts, understand the concepts, because that is the foundation for so many other subjects like computer architecture, operating system, system software, so on and so forth. Many subjects, and even in the recruitment process also, in the written test and in the interview, most of the questions, at least 20 to 25% will be based on this computer organization subject. So please take it up seriously. Don't mug up the things, and try to understand the concept and do well in your exams. I thank wholeheartedly Indu Jain, Salangai Naigi, and Veena Bhatt for taking up this course, and wish them all the best. It runs very well for 3 days. And over to the 3 faculty, the resource person, and I wish you all a knowledgeable 3 days spent ahead. Thank you all. Have a good day.
Uh, Very good morning, everyone. Sorry for the interruption. Myself, Indu B. Jain from the Department of CSE Assistant Professor, along with my co-faculties Veena Bhatt, Salagai Nayagi Madam. We wholeheartedly thank our management, our principal and HOD, Dr. Lata CA Madam, for motivating us and giving us an opportunity to conduct such events which helps our students boosting their confidence well before their examinations. Without wasting much time, we shall start our session for the day. Uh, Good morning once again. We have planned our schedule to wrap up the entire 5 modules in 3 days schedule. To begin with, the day one, that is today morning from 9:30 to 1 o'clock is what we have planned. So we are here to cover up the first two modules. To begin with, the basic structures of computers and IO organization. Moving ahead on the second day, we have very thoroughly gone through the syllabus and designed in such a way that we should be very crispy and the content should be covering up the entire module, but nowhere we are missing out any of the contents. To begin with the second day session, it will be memory systems, basic processing unit. Along with that, we have planned to discuss upon the virtual memory concept, which is beyond our syllabus. That comes under the content beyond syllabus. On the day 3, that is on 25th February, morning session 9:30, we have designed the session in such a way that the entire the half a day session will go with the arithmetic operations, which is the 4th module according to your syllabus. We have planned in such a way that the every problem or every algorithm in this module will be covered up in detail. So we are happy to welcome all your doubts at any point in time. Please do feel free to share any of your doubts at any instant of time, and we'll stop and address your doubts. To begin with the module 1, the basic structure of computers. As we are all aware of the term computers, so computer basically is an electronic machine, as we all know. This electronic machine, of course, help us, dealing with all the computations, calculations, and other aspects of the digital world today. So to begin with the functional units, as we all know, at fundamental aspect of the computer deals with the input, output, arithmetic logic unit, control unit, and of course, very important role played will also be the memory. So this memory unit happens to be the intermediary which picks up the input, accesses, passes it across to the processor for any further calculations, right? So these are some of the functional units of the computer. To begin with the input, we all know the input units deals with picking up the inputs from the end user. Okay, so there are various input devices available, joysticks, keyboard, which is more often being used, all right? So moving ahead with the memory. So what is the role played by the memory? As we all know, memory is basically intended to store the contents, right? So how long will it store or when does it store? In the beginning of the processing, it picks up the data that is sent from the user, stores for some time, or it immediately passes it across to the processor for any further processing. All right. So once it has been passed across to the processor, depending upon the operation, what has been demanded by the end user, the arithmetic and logic unit will be triggered. So based on the operation, what has been asked by the end user, the operation correspondingly will be executed. So as we can see, these functional units, that is input, output, memory, or arithmetic and logic unit, all needs to have to communicate and coordinate with each other. So these units, in case they have to coordinate to any further communications, the control unit plays a very vital role. So this control unit controls and coordinates all the communication across the functional units. So moving ahead, we shall see the basic operational concepts. So these basic operational concepts actually intends in identifying what is necessary when we pick up a very simple operation, like for example, as you can see from this screen here, we have a small tiny pseudocode that does the sum of two numbers. Sum of two numbers, sum is equal to A plus B. So here, all the three terms, that is sum, A and B, are all, termed as a variable, right? So these variables actually help us perform the operation. So how is it going to be dealt in the memory, whether it is being stored consecutively or at different locations in the memory? So to make this point very much clear and apt, here you can see the diagram which shows the memory location addresses. So 4000, wherein the variable A will be stored, variable B at 4004, and finally the sum, yeah, so 2008. Right. So what operation we are performing here is the sum. That is a simple arithmetic operation, A plus B. Right. Finally, after computing the sum, the result will be stored in the memory location sum. All right. The result here is, of course, 11, computing 5 plus 6. So here comes the ALU's action, which picks up these two variables values and computes the result and stores it into the destination or resultant variable called sum. So this looks quite simple for us as an end user, but internally in the computer, lot many things actually happens, picking up the input variables and storing the corresponding variables into the memory location and transferring it into the processor for further processing. Once the processing is done, the result will be sent back to the memory location. Right. So this is how the overall operational concept can be viewed. Simple operation we have picked up here to make it very clear for your understanding. Right. So moving ahead. Yeah. So we will get a clear picture as to how the connection between the processor and the memory can be seen, and it can be witnessed from this diagram clearly. As you can see on one phase of the diagram, you have the memory and the input-output units. On the other end, we have the processor. On whole, this one entire block actually is the processor. On the other hand, it is the memory and the output. And you can see there is a line running in between the memory input output and the processor, right? So this happens to be the bus, which is helping us connecting the various functional units of the computer. So this diagram typically addresses the connection between the processor and the memory. All right. So as you can see, along with the ALU, memory, input, output, and control unit, we also have certain other registers that plays a very, very vital role in computing the, or you can say, performing the operation. So from this pictorial representation, it is quite evident there are certain registers which are termed as MAR, MDR, PC, IR, and the register starting from R0 till Rn-1. So these are the various registers which helps us perform the operation. So we shall deal with these registers in detail in a short while. All right. So these are the registers which we were able to witness in the previous diagram. So to begin with, the first register, instruction register. So what is actually the role played by the instruction register? As the name indicates, here you can see the IR register holds, or it helps us hold the current instruction, okay, which is under process, that is, which is under execution. All right. Moving ahead, we have this register called PC. PC stands for program counter. Program counter is the register which holds the address of the next instruction that needs to be fetched and executed, right? So every time a particular instruction is under execution, the PC gets updated immediately. Moving ahead, we have the general purpose registers starting from R0 till Rn-1. These general purpose registers are the registers which are dealt or which are being used for holding the operands and the results. After computing, the results also can be stored using these registers, and hence the term general purpose registers. Then we have these two special registers called memory address registers and memory data registers. As the name indicates, they are quite simple and evident. They say memory address register, MAR. So they are intended to hold the address of the location to be accessed, right? We have this MDR, as I mentioned earlier, they do specify the task what they are supposed to be. That is, it holds the data. It contains the data to be written into or read out of the addressed location. MAR, MDR, general purpose registers, IR and PC. So these are the important registers that is a part of the processor which helps compute the action. So understanding the basics of what registers does and what are they meant for, we shall understand what the basic operating steps are. So these basic operating steps actually helps us understand more in clear how the input actually is been sent from the user, how the PC gets updated, what is the role of MAR and MDR, much in detail. So to begin with, the programs that we have to code in will be sent through the input devices, and that for a time being will be residing in the memory, So what happens to the PC and what is the role the IR actually takes? As I mentioned earlier, IR always and every time holds the address of the current instruction or the instruction that is under execution, right? So what should be the PC then? As already mentioned again, PC holds the address of the next instruction to be executed. So that is all fine. But at the beginning of the instruction, what should be PC containing? PC always will be set to point to the first instruction. The moment the first instruction is picked up from the PC and stored and the corresponding instruction gets executed, then PC immediately gets updated with the next instruction. So the contents of the PC, what was stored earlier, will now be transferred to MAR, Memory Address Register. So from here, the read signal will be sent to the memory, indicating the memory that the instruction that needs to be processed is ready and it is available in the MAR register. Okay, so once the first instruction is read out and loaded onto the memory, that is MDR, that is Memory Data Register. Now, now that we have understood what is the address of the data and where exactly it needs to be stored. So now what to be done? It needs to be then processed, right? So the processing happens by reading the contents of the MDR, and that needs to be transferred across to the IR register. Once it has been moved into the IR register, it gets decoded and executed. So this is how the operations of the computer actually deals with. So PC gets updated every time the new instruction is completed its action. MAR and MDR gets updated correspondingly one after the other after picking up the instructions. Yeah. So as I mentioned earlier, now that we have fetched the address of the next instruction updated in the PC, MAR and MDR also got updated. What next? Now that we have understood that it has been decoded and it is ready for the execution. All right. So once it is ready for the execution, which unit should be triggered? Of course, it is ALU, that is arithmetic and logic unit. So while it has been triggered, it demands for the operands. What operands? Say suppose we are performing sum is equal to A plus B. Here the variables or the operands A and B happens to be the operands. The values of these operands has to be fetched and sent across to the ALU. All right, and that can happen through the general purpose registers, or you can make use of the memory as well. Right, once the operation is done, okay, once the operation is done, what next? We are supposed to store the result back. Where are we going to store the result back? We are storing back into the there are two options where you can actually store the result. It can be into the general purpose registers or into the memory. Okay, so while this is happening one by one, step by step, every time the PC gets incremented and the PC gets updated with the address of the next instruction, gets updated with the address of the next instruction. Moving ahead, let us now understand the bus structures. Till now, we understood the internal parts of the processor. What are the various units that are a part of the processor and various registers. Now we shall see how the bus structures plays a vital role. So to understand the bus structures well before, we need to understand what the bus is. So the bus basically is a set of lines, or you can call it as group of lines that serves as a connecting path for several devices. It acts as a connecting path for several devices. So that happens to be the definition of the bus. It is just a group of lines that serves as a connecting path for several devices. So we have three different forms of buses, that is address bus, data bus, or control bus. So as these three buses are quite self-evident, that says address bus is the one which carries the address, data bus is the one which carries the data, and of course the control bus carries the control information, right? So they are intended to perform each one of the tasks independently. So the address bus carries the address from where it is coming or to where it has to go. The data bus carries the data, that is the operand values, and followed by we have the control bus which carries the operation to perform, whether it is a read operation or write operation. Okay, so here comes the bus structure. We have this bus structure called single bus. Of course, we have multiple bus operation that we will see in the coming sections, right? So here comes the very simple single bus structure. As you can see, there is a single arrow line running across the various units of the computer. To begin with, you have the input, you have the output, memory, and the processor. These are the fundamental units of a computer, as we all have witnessed already. So the input unit is supposed to give the data onto the bus, and the output unit is supposed to take the data onto the output unit. And the memory actually has bi-direction connection with the bus. And for the simple reason that you are accessing the memory to store the data, also to retrieve the data. And hence the arrow key here indicates bi-directional. Also with the processor, as you can witness here, we have the bi-directional connection between the processor and the bus. So it indicates again, you are allowed to either access the data or you can also send the data across. So in order to access all this information across the various fundamental units of the computer, we do access in the form of a byte or word. So I guess this is the information that you are already aware of. 1 byte takes up 8 bits and 1 word goes up to 4 bytes. That is 32 bits. So whatever the bus structure we pick up, there is always a challenge. There is always a challenge. What challenge? That means, say, if multiple devices are connected across using the bus, there is always a speed issue. What kind of a bus that you have made use of matters a lot in the overall performance of the system, right? So there are different devices that have different transfer or the operate speed, right? So when we compare the processor with the other devices, input or output devices, the processing speed at which the processor works is definitely much faster compared to any other hardware devices. And hence, we do have to have a balance between the normal or any devices or peripheral devices with that of the processor or any other devices. Because the challenge here is to manage and maintain the balance between the transfer rate or the operating speed, right? So if the speed of the bus is bounded by the slowest device connected to it, right, then the speed of the bus definitely will not have any control. So that way the efficiency will be on the performance of the computer, or the efficiency of the processor will be low. So how are we going to deal with this problem? We have to deal with this problem by bringing up a concept called as buffers. So these buffers are basically used for temporary storage. So when we make use of these buffers, they actually bring in a balance between the speed difference or transfer rate difference between the devices and the processor, so that we can make sure that the processor is not waiting at any point in time, and it can be put into action all the time. Yeah. So we shall see how the performance of system actually matters. All right. As we all know, the simple term performance means that the throughput, that means how best you can extract, or what to what extent you can utilize the system's speed, right? So the performance is the important measure of a computer, how quickly it can execute the programs, right? So we cannot afford to spend the whole day to compute one single program, right? So the processor has its own speed, and of course the other devices which are connected to the processor also should manage and balance with the speed of the processor. And as we witnessed from the previous slide, that we have to make use of the buffers to deal with this difference. So what are the factors that affects the performance? Of course, more or less, we have touched upon this point in the previous slides. Here we will look back again. It is the hardware design that we make use of, right? So the type of the hardware that you make use of, and the connecting, that is the buses that we make use of, matters a lot in improving or degrading the performance of the computer on the whole. Right, so the hardware design plays a very important role in boosting up the performance of the system. Likewise, we also have the instruction set. So this instruction set, it can, in two different forms. Let's say we have one operation to perform. You can either make it simple, or complex. So simple, I mean to say, break down the operation into various simple steps. Thereby, each instruction is quite simple, but it is building upon the number of instructions, or you can say the number of instructions gets increased. On the other hand, you make it simple, that is, you reduce the number of instructions, but each instruction is quite complex. So there are two instruction set formats that we will address at the end of this session, which is CISC and RISC. CISC and RISC actually stands for Complex Instruction Set Computers, and RISC, RISC, indicates the Reduced Instruction Set Computer. All right, more in detail about this will be dealt at the end of the session. So we shall see that later. So the other factor that affects the overall performance of the computer is the compiler. So as we all know what compiler does. Compiler is basically breaking down the higher level language programs into machine understandable language, right? So the type of the compiler that we make use of definitely affects the overall performance of the computer. Yeah. So we will equate this basic performance with respect to the time it takes, with the number of the instructions that we make use of, and the average number of steps that is needed to perform an action, and the overall clock rate. All right. So the basic performance equation goes with T equals N. It is the product of N into S divided by R. So here are the different terms that are a part of this performance equation, basic performance equation. T actually stands for the processor time required to execute a program that has been prepared in a high-level language. Yes or no? The high-level language that has been written in the form of a program should be broken down into the machine understandable language, and of course it incurs some time. So that is the processor time indicated by capital T, followed by N. N happens to be the number of actual machine language instructions needed to complete the execution. Right. So as I mentioned in the previous discussion that an operation, given an operation, can be broken down into various steps. So as the number of steps you divide, depending upon the complexity of the operation, the N, that is the term N, actually increases. Right. Followed by S. So this again plays a very vital role. It happens to be an important factor to improve the performance of the system. So which stands for average number of basic steps that is needed to execute one machine instructions. It is the average number of basic steps needed to execute one machine instruction. So each step completes in one clock cycle that is denoted by R. So in one clock cycle, we are expecting one complete step to be completed. So that is indicated by R, the clock rate. So the clock rate can be related to the period, or you can say the length of the clock signal. Here P indicates the period. So R is equal to, that is the clock rate is related to the period with the inversely proportional relation, that is 1 by P, where P happens to be the length of the clock signal. And this is actually measured in hertz. Okay, number of clock cycles per second, unit of R. All right, so the basic performance equation goes with T equals N into S divided by R. Okay, so the performance measurement to deal with, in the previous slide, we saw that the basic performance equation. Here we shall witness how it can be measured, and there is a corporation that actually monitors the overall performance of the system, and that is SPEC. Okay, and we generally call it as SPEC rating. SPEC stands for System Performance Evaluation Corporation. Okay, this basically selects and it publishes the representative application programs for different application domains, along with the test results for many already existing computers in the market. All right, so the SPEC rating can be related with the reference computer to that of the computer under the test. With this relation, SPEC rating is equal to the running time required for a computer that is on the reference computer over the running time on the computer under test. So we are here basically evaluating the performance of the computer which is under the test. So we need to have a benchmark in order to understand how best the system is performing, and that has been given with the SPEC rating, SPEC. So System Performance Evaluation Corporation. Right, and this is related to the equation phi with the SPEC to the power of 1 over n, ranging between the value of I is equal to 1 till n. Of course, from the examination point of view, this is quite important. You'll be asked one question on this about the SPEC rating. Okay, so moving ahead with our next discussion about the machine instructions, programs, memory locations, addresses, and operations. In this entire discussion, this happens to be the second chapter of your textbook. Here we'll be dealing more about the machine instructions, the programs, the memory locations, how are we going to access them using the addresses and various operations. Yeah, to begin with, we need to understand how memory location is actually organized, or how we can view the memory. As you all have understood at least the basics of the memory, that it helps us store the data, and also it helps us, it allows the user to access the data from the locations, right? So the memory consists of millions of storage cells. So each of these will be capable of storing 1 bit at a time. 1 bit at a time. So here, each memory location will have definitely the address, because while we are storing, or while we are retrieving the data from the memory location, each needs to have a particular address, right? So the data that is stored in the memory will be usually accessed in an n-bit groups, that is in a group. You are grouping all these n-bit together to form the word. Okay, and the number of bits that is a part of this group is called as word length. So from this diagram, it is quite evident that we have one block. As you can see, there are n number of bits, and each this n number of bits together forms a word. Okay, so we have first word, second word, likewise ith word, and finally the last word. All right. So we shall see and understand how the memory location is organized in a sequential manner in the coming slide. Right. So just now we understood that n-bit bits are actually grouped to form the word, and the number of bits that are a part of that group is called as word length, right? So let us see and understand how the word is actually represented. So here the word is represented with a 32-bit word length, and here is an example of that. And as you can see, this word length starts with bit 0, followed by bit 1, likewise bit 30th and bit 31st. So here the 31st bit, the last bit of the word, actually plays a very vital role. What is that? See, D31 bit, if at all the data that you store in this particular location of the word, right? If it is a 0, it means that the data what you have stored here, or the number what you have stored here, is a positive number. All right. Likewise, if you have a bit value as 1 at the 31st bit, then it indicates that the number is a negative number. So this is how the word representation can be done, and it is of 32-bit word length, starting with B0 till B31. So 31st bit actually indicates whether the number is a positive number or a negative number by the value that it actually stores. 0 for the positive number and 1 for the negative numbers. So now that we have understood how the memory location is actually organized, and how the word length actually looks like, or the word actually looks like, the representation of the word, let us move ahead and understand what are the addresses. So we all have come across this term address, and we know what it actually means, right? Of course, these addresses are a very important part of the overall computation, because having individual bit locations in the memory, having a distinct address makes no sense, right? So, and also it is quite impractical, right? So what do? We group them in the form of a bytes or word. So all these consecutive bits are grouped together to form a byte, or all these bytes are grouped together to form the word. So there are two forms of addresses, one being the byte addressable memory and the word addressable memory. So the byte addressable memory and the word addressable memory helps us, to refer the memory locations. And of course, they do have distinct addresses on its own. Okay, so we shall understand how these addresses, or that is the byte addressable memory or word addressable memory, plays a vital role. Yeah. Here comes the word assignment, or you can say the byte address or word address assignment. And the standard two forms of assignment are big endian and little endian. So the big endian and little endian are the two different forms of assignment with respect to the word addresses or the byte addresses. To begin with the big endian. So this big endian representation always goes with the lower byte addresses. The lower byte addresses are always used for the MSB, that is most significant bytes of the word. So as you can see here, big endian representation, the lower byte addresses, that is 0 and 4 here from this pictorial representation, the lower byte addresses are used for the most significant bytes of the word. Most significant bytes of the word. As you can see, on the other hand, we have this little endian representation, which is just the opposite of the big endian. That is the lower byte addresses. As you can witness here from the diagram, the lower byte addresses are used for the less significant bytes of the word. It is 0 and 4. Right? And let me make this point more clear here. This big endian and little endian assignments are more often asked in the question paper. So please pay more attention towards this representation along with the what they actually mean, that is big endian and little endian representation. Along with these two diagrams, you are supposed to write. Big endian and little endian more important from the examination point of view. So please pay more attention towards this. Slide. So moving ahead, we have two operations. What are those? Memory operations. So in order to have access to the memory, there are two major operations that helps us in accessing the data that is stored or residing in the memory. So those two operations are load and store. As the name indicates, load means you are actually loading the data onto some location. So in this regard, in this conversation, of course, it is the memory that we are dealing with, and hence we are copying the content from a memory location to a general purpose register. Okay, general purpose register. So you are either reading or fetching the data from the memory location. Likewise, we have store. So this store deals with writing, that is copy the content from the register to the memory. So these are the two major operations that is a part of the memory, loading and storing. Generally, you tend to get confused with this. So be very clear about this. Loading is for reading or fetching the data from a memory location, from the memory location to the general purpose register. And storing is for writing, that is copying the content from the register to the memory. Okay. So, moving ahead with our next discussion, having understood the basics of the computer fundamental units, functional units, understanding what, how the memory is actually organized, and what are the various operations that are a part of the memory, that is load and store, we shall step into the instructions and instruction sequencing. So this helps us understand what basically the instruction is and how is it being actually sequenced. Okay, so before we actually dig into the major operation that is a must to be performed, let us understand what the instruction is. As we all know, the instruction is a protocols. It is basically your instructing the system to perform a task, right? So such instruction or instruction sequencing is very much essential in order to make sure the task is complete, with the result, or you can say expected, as expected. So here comes some of the most important operations that is to be performed. Okay, to begin with, for any task to complete or to begin any of the operation, first and foremost, we need to have the data. right? So this data needs to be transferred between the memory and the processor registers, right? So the data may be residing in the memory that needs to be pushed onto the processor registers, all right, in order to get the task done. So once the data is ready in the processor registers, we can then have the ALU being triggered. That is, arithmetic and logic operations on the data can be performed. Okay, and while this is happening, all the instructions or the programs that we have coded in needs to be controlled and coordinated one after the other. So sequencing of the program is very much essential. Right. So after this, of course, we do have the processing done with the instruction. So we may have to tend at the end, to transfer the data. Once the data has been processed, it is now the information that we have in hand that needs to be again stored back to the memory. Right. So these are the 4 major must perform operations that should be done. I shall repeat on that. It is initially to data transfer between the memory and the processor registers, followed by the arithmetic and logic operations on the data, program sequencing and control, and finally the IO transfers. Okay. Fine. So in order to have all these operations performed, we do have certain notations to deal with. That is, in the very first step in the previous slide, as we saw, it is the data transfers between the memory and the processor register, right? So it can be in the form of register transfer notation, or we have assembler notations. So that we will see shortly. To begin with, the register transfer notation, in short, we call it as RTN. So this RTN actually helps transfer the data in the, making use of the registers. All right, having registers in hand, you can make use of those registers to transfer the data across. So here we can identify a location by a symbolic name. So that symbolic name actually will be, representing the hardware binary address, right? Which can be LOC. It is a standard location. Notation to represent the location in the symbolic name. So R0 till Rn minus 1, as we discussed in the previous slides, that they belong to the general purpose registers. So we do make use of these general purpose registers for having the register transfer notations. So here, the contents of a locations are denoted by placing the square brackets around the name of the location. As you can see in this example, if we have this square brackets mentioned along with these notations, indicates that the location value that we are representing. If you do not have this square bracket, means that you are actually representing that register. But here this square bracket actually indicates the contents of that particular register. So in this example, what are we doing? And also, as you can witness, there is an arrow key towards the register R1. That means the contents of the memory location LOC is now being transferred to register R1. On the other hand, one more example here, which does the addition of the contents of R1 with the R2, the contents of R2, and finally the result is stored in the register R3. All right. So this is how we represent the register, that is RTN, register transfer notation. Okay, followed by we have assembly language notation. As you can see, the operation that we perform is actually written in the form of directives, or you can say the words in the form of the word. That means you're trying to move the contents of the location R1 or LOC, and we have the operation here add R1, R2, and R3. So these are the instructions that represents the instructions of the program. Right. So the first instruction move LOC comma R1 actually indicates the contents of LOC is now moved into the register R1. Likewise, we have another example here to show how the operation is performed, that is adding R1 with R2, and the result is being stored onto R3. Okay, so in this example, we have come across certain representations. So anything related to LOCA, PAR1, and if you find PLACE, so all this comes under the memory location representation. And we have this registers R1, R2, and R3, and you can go up to Rn minus 1. And of course, we also can come across various IO registers that includes data in, data out, out status, and in status. So these happens to be the IO registers. So we clearly understood what the RTN is, that is register transfer notation, and we understood what the assembly language notation is. Moving ahead, we will see how the CPU is actually organized. More or less, we have already come across in our previous discussion, the first few slides, the various registers that helps us perform the action. To some more adding on to those registers and or you can say the buffers, here we come across certain other aspects of CPU organization. To begin with, the accumulator. So what is this accumulator? So whatever the operation that we perform generally, accumulator will be, used to save it into the memory very often. Okay, accumulator has to be saved to the memory quite often. And here the result also, you can call it as an intermediate result, generally goes to the accumulator. Okay. And we also have the support of the general registers, that is you can term it as general purpose registers. So these registers holds the operation and basically helps us in reducing the overall memory traffic. Okay. So otherwise, the other form of storing the intermediate, data, or you can say contents, we can as well make use of the stacks. So these stacks actually helps us store the, more often we do make use of the written address to be stored into the stacks. Otherwise, stacks also helps us, store the operands and the results at any point in time of the, operation being performed. Yeah, so here comes the various instruction formats. The various instruction formats happens to be, into various categories are there, but we shall cover a few of them. 3 address instruction, 2 address instructions, and 1 address instruction. So what does this 3 address instruction, 2 address instructions, and the 1 address instruction indicate? As the name itself is evident, 3 address, meaning what? We have 3 different variables that needs to be addressed, and the operation is performed here. So we do make use of 3 different variables here to perform the action. So here you can see an example: add A, B, and C, indicating that you're adding A, B, and C, making use of 3 different variables. Followed by, you have 2 address instructions. As the name indicates, it says we have 2 addresses instruction, that is A or B. We do not have the third variable here. For any operation that we perform, we do make use of these 2 variables alone. Okay, so there is another form of 2 address instructions. In the previous discussion, we just made use of these operands, and here we can as well involve the memory locations, or you can also include 1 register along with this. So here is an example. So move A, R0, you have add B, R0. Another example to demonstrate here is move R0, C. Okay. So here we have the involvement of 1 memory location, as you can see here, and 1 register as well. Yeah. Lastly, we have 1 address instruction. This 1 address instruction says, as the examples here are quite explanative. That is A, B, and C in these 3 different instructions. A, while loading, add B, store C. So what is the other? What do you say, the operand that has been a part of this? So we do make use of the accumulator here. We do make use of the accumulator in this case to store, add, or load. All right. So these are the 3 important forms of instructions that we come across. Yeah. So moving ahead and understanding much better about the straight line sequencing of instruction execution. So here, to understand this much better, we need to have the basics of the instruction sequencing that we have already discussed in our previous slides. So instruction execution and straight line sequencing actually deals with how the instructions are being stored in the memory. Okay, so what are we going to assume? How are we going to assume the various instructions that are a part of the memory? To begin with, one memory operand per instruction will be stored or restored, you can say. All right, and each of which will be of 32-bit word length. Each of which will be of 32-bit word length. All right, full memory address can be directly specified in a single word instruction. As you can see, this is one single word indicating ith position, I plus 4th, I plus 8, and so on. All right. So to have this instruction being stored, these are some of the assumptions that we need to make. All right. So this entire process of instruction execution falls into two different phases. So two-phase procedure is instruction fetch phase and instruction execute phase. So the first thing is instruction fetch phase. So what do we actually do in instruction fetch? As the name indicates, we are fetching the instruction wherever it is stored. We are trying to fetch the instruction. So to perform an action, first and foremost, we need to have the instruction in hand. So that happens to be our first phase, that is instruction fetching phase, followed by followed by instruction execute phase. Instruction execute phase. Okay, so instruction execute phase, wherein now that we have the instruction in hand, we can execute the instruction by triggering the corresponding unit, that is ALU. Okay. Yeah. In the meanwhile, I have one query from your end. What does move actually means? MOV. Actually, it can work as load or store. It can actually help working as load or storing. All right. So you can either load the data onto the memory or pick the data from the memory. So move can perform these two actions. All right. And and you can as well copy it as being used. It is being used. So it just to move the data between the source and the destination. Move is basically used to move the contents, or you can say move the data between the source and the destination. Okay, happy to see you some of the queries in the chat box. Yeah, we shall keep it more interactive. You can have questions, whatever you have, you can just put into the chat box. We shall address it timely. Thank you. So we were discussing about the instruction execution and its sequencing. So to begin with, we have the sequential, that is straight line sequencing, or in other terms, the instructions are being executed step by step, right? Step by step. So this happens to be quite simple to understand at the basic level. That is whatever the operation you are trying to perform, you are breaking them down into simple steps. So each one such instruction is stored in each memory location, starting with I, moving ahead with I plus 4, I plus 8, and so on. So what are we trying to do in this particular sequential you can say instruction execution is, we are performing the action of operation in sequence, right? Say suppose we are asked to add the two numbers. We can comfortably add because it is finger countable. Maybe yes, at next instant we'll be asked to add 10 numbers. Of course, to an extent it is reachable. We can do it, write it down and do it. And this is what the sequential representation actually you can see. We have move num1 to R0, then add num2 with the R0. The contents of R0 will now be added to num2, right? Now num2 holds the final result, and again we have next instruction add. So likewise, if you have 10 different numbers, to add those 10 different numbers along with the register, general purpose register R0, we are adding with the number and finally storing the result in the particular register, right? So every time we are adding, the previous the value of the number will be updated, or you can say overwritten, and the new one will be stored. Finally, after all the n numbers have been added, we are now moving the final result that is stored in the R0 to the resultant variable sum. So this is a simple example showing adding the numbers num1, num2, num3 till number n. Okay, and we are making use of the general purpose registers R0, and the final result is being stored onto the sum, right? So here. What is the advantage of making use of sequential way of executing the instruction? Of course, it is quite simple. It is being done in stepwise, one by one. So if you want 10 numbers to be added, 10 different steps, 20 numbers to be added, 20 different steps. And of course, if the numbers increase, the number of steps also gets increased. So you think so it is advantageous? Definitely not. Of course, it is quite, good for the instructions which have simple terms and simple number of steps. Otherwise, when large number of values or operands or numbers are being involved, then making use of sequential way of executing is not definitely advised. So this is how the sequential or straight line sequencing actually happens for adding n different numbers. So how we can address this problem? We can address this problem, or we can reduce the number of steps involved in this program or the instruction by introducing something called as branching, or you can call it as looping, right? So in the previous discussion, we saw n different numbers were supposed to be added. So what we did, we actually coded n different steps, but that is not quite advisable because the number of steps were increasing, right? So to overcome that, we have this concept called looping. So looping actually helps us perform the action with just one instruction, but calling the same instruction multiple number of times. How many number of times you are calling? As the number of numbers have been mentioned in the instruction. If you have 10 numbers to be executed, yes, 10 number of times the instruction gets executed in a loop, or iteratively it gets executed. Finally the sum is actually stored. I mean the resultant that is stored in the R0 will now be moved on to the sum happens to be the resultant variable. And yeah, the representation of these operands are all same as for the sequential instruction execution. So only difference here is we are making use of branching. How are we going to deal with this? You would begin with move n to R1. Okay, so move n to R1 actually says R1 contains the n contains the number of steps, or you can say the number of instructions that is a part of the program. So every time one single instruction that has been executed, the number that is the register R1 content will be decremented by 1. So as and when this number is getting decremented every time one loop or one iteration is complete, then soon after that it is compared with the branch. That is, branch is greater than 0. So this variable actually indicates that the branching or looping should happen as long as the value is reaching 0. The moment the value reaches 0, that is R1 reaches 0, you need to stop. Okay. If at all, if it is greater than 0, again call the loop. That means perform this action multiple number of times. Perform this action multiple number of times until and unless you end up getting the result, and that is being stored in the sum. Okay. So move here again plays a vital role. As I said, it can act as a load or store operation. Okay, so instruction execution can be of two different ways: sequential execution or branching. Okay, we understood how branching is advantageous compared to the sequential way of executing. Okay, yeah. Here comes the condition codes. What are these condition codes and why are these actually used? Of course, while we are performing the action, as we saw in the previous discussions, various results were generated. So these results plays a vital role in taking up the next instruction. So these results are stored in a separate code, or you can say flags you can call, or code registers you can as well say. Of course, we do see in many places these condition codes being termed as status registers. So these status registers can be of 4 different kinds: negative, 0, overflow, or carry. N for negative, Z for 0, V for overflow, and C for carry. So what does these actually indicate? See, these are the condition code flags. So these condition code flags have been used to represent what result we have generated. That means what result did we get after performing the operation. Because in the word length we have seen that the 31st bit actually was indicating the type of the result, that is the number. If the B31st bit was 0, it was called as negative, and 1, I mean 1 is for negative numbers and 0 for the positive numbers, right? So based on that value, we are setting up these condition code flags. So N for negative, that means if the result generated is negative value, then N is actually set. If the result generated is 0, then Z code flag will be set. Likewise, we also have this carry and overflow flags being set, and we come across these two condition code flags while we are performing the arithmetic operations like adding. Generally we tend to get the final result being overflowed. Okay, in such cases, V flag, that is V condition flag, will be set. Likewise, the carry flag. Yes, so while we are performing the addition, intermediate carry needs to be sent across to the next bit for performing the next action, and henceforth the C flag also will be set while we are performing the arithmetic operations especially. Okay, so these are the different flags that actually indicates the various condition codes or the status of the operation. All right. Okay, so yeah, let me interrupt at this point in time. I have a query in the chat box asking for repeating the branching. Yes. Maybe you have come across the term looping or iteration in your C. We have come across these terms like iterative or processing this number of steps repetitively, right? Same thing holds good here. Branching is jumping from one instruction to the other and performing the looping, right? So here looping actually does this particular loop statement or flag actually picks up the action. What action? Determine the address of the next number and again add. Okay, I just gave you the comparison between the sequential way of instruction execution, wherein we had all the instructions being done step by step. If there are n different numbers to be added, n number of steps. While we have to avoid the number of steps, and hence we do bring in the concept of looping, or you can say it as, you can call it as branching. So what are we trying to do here is we are performing the same n number of values addition. Okay, n number of value addition, but as you can see from the previous diagram, here we had 1 plus 4n number of steps. While in this case, no, hardly we had 4 different steps to complete the entire task, be it the number of values being 100, 200, and it can go beyond, right? So to begin with, you actually start with the number or not. Okay, and R1 actually takes the number of values that are a part of the instruction. So every time one number is picked up for execution, this R1 gets decremented. So the moment R1 gets decremented, it immediately goes to the next step, checking for whether branch is greater than 0. What is this branch? It is a condition. You are checking for the condition. If the value that has been decremented is greater than 0, then again you need to loop. That means perform the addition operation again. So the moment this instruction is called, the loop, the flag, as you can see, loop, it gets branched up to the statement here. There's a flag, you can see. Loop, it says determine the address of the next number and again add. So this step actually continues for n number of values. As a number of values gets decremented every time the condition is checked. If the branch is greater than 0, only then you continue to do the looping. Else come out of the looping, and then finally the result will be stored in R0. That is actually was intermediately stored in R0. Now will be transferred across to the sum. Now the sum will take up the final result after adding n numbers. After adding n numbers. Okay, so I guess I've addressed your doubt. If you have anything else relating to the instructions, execution with respect to the sequential and branching, or anything till now, whatever we have covered, you're happy to address your doubts. Okay, yeah, fine. Thank you all. I shall now hand over to Professor Veena Madam to continue with our addressing modes. Thank you all for your patient listening. Thank you.
So good morning all. This is Veena here and I'll be starting from addressing mode. Addressing mode is very important topic, one very frequently asked in exam. So as all of us know, instructions works on data operands. The most commonly used data operands are variables, constants and pointers. For example, in sum is equal to a plus b, sum a and b are data operands. Now in our computer system, these data operands can be in register or it can be even in memory location. So addressing mode, it is actually a different ways in which you say the location of these operand. As I have already told, these operands can be in the register or it can still be in the main memory of our computer system. So every instruction needs data operands. And as I have already told, the common ones are variables or the constants and the pointers. There are some doubts in the chat box. I will take some time and then I will start addressing them. So there are different types of addressing mode. There are 7 of them in our syllabus. The first one is called as register mode. Here, the operand is nothing but the content of a register. As the name only says, it's a register mode and the data is actually in processor register. And the name of the register, you will have to mention in the instruction. Now, example I have taken here, add is an operation that works on these 2 operands. Now, operands here are present in the processor register. For example, always this is a source operand and this will be the destination operand. So R0, it is one of the processor general purpose register. You can see here the data is 9 and R1 right now is 4. So we are asking them to be added. Add R0, R1. So it is 9 plus 4, 13. So as I have already told, this will be destination. So after the successful execution of this instruction, R1 will be holding 13. That's a sum of R0 and R1. So if you are naming the register in the instruction, then the mode is considered as register mode. Let me just check. There are some doubts I can see in the chat box. If they ask in the exam, I think this is for the branching. This doubt was for the branching. They usually ask you to describe the branching along with the example. The same example of adding n numbers of integers you can write. Because throughout this module, we are taking 2 examples. One is adding n number of integers. Even for the addressing mode also, I'll be taking the same example. So after the register mode, the second one is direct or absolute mode. Here the operand is present in the main memory. It has still not come to the processor register. The operand or the data is still in the main memory. See, as I've written, the operand is in a memory location. These are the example instructions. Move A, R0. That means I'm requesting the data which is present in a location, that is A, to move to a processor register called as R0. Already we have told you R0, R1 to Rn-1 you will be using for the registers, and A, B, C, any alphabets or variable VAR or place, these letters you can use to denote a memory location. So here there are two operands. This is source and this is destination. And you can see that source operand is in absolute mode or direct mode, and the destination operand is register mode, because there I named a register. But the first operand, this is in the absolute mode. I have the second instruction, add A, B, where both the operands are absolute mode or direct mode. Both the operands are in absolute mode. Both the operands of this particular instructions are still in the memory. Move location, R0. See, location, as I said, still denotes the memory, main memory. So here also, the first operand is in the absolute mode and the second operand R0 is in register mode. Now, here I have taken something called as EA. EA stands for effective address. Effective address is actually the address where you can get the data. Now here the address is nothing but I can get my data in the register itself, which has been named. So that is RI. I means it can be 1 to 0 to n-1. In this case, address is nothing but the memory location, whichever you have mentioned in the instruction. So these are the first two addressing mode. The third one is immediate mode. Now, in case of immediate mode, now here it is used for the constant. The operand is immediately or available in the instruction. Now, you can see here, the source operand, I have used immediate mode. Only for the source operand, I have used immediate mode. You can see the data explicitly in the instruction itself. So in the first one, in the register mode, data was in the register. In the second one, in the direct mode, the data was in the memory location. Here, the third one, that's the immediate mode, data is a part of instruction itself. So you have to take a constant value in this particular mode. Whenever you are taking a constant value, now here, as all of us know, we write our instruction in assembly language. In assembly language, any constant when you are taking, you will have to add this hash symbol. Okay. Then I have mentioned here, this immediate mode we can use only for the source operands. We cannot use this mode in the destination. So the destination, it has to be either a register, or it has to be either in the register mode, or it has to be in the absolute mode. I have one more example here. I'm using add. I would like to add 20. That means 20 plus 30, and the answer I want to save it in R1. So that is 50. That has to be saved in R1. Next, we have, as I said, the commonly used data operands are variables, constants, and the pointers. So now we are coming to pointers. Now this is the mode which we use when we have array of numbers. So sometimes we may not be interested only in one value. We may be having an array of 50 to 100 integers, or it can be anything. So when you are handling arrays, we need to make use of these pointers. So in case of indirect mode, I just explained with the example to make it a little easier. So here is the instruction, move. Now the R2 we have shown within the bracket here. So this is the difference between the register and the indirect mode. Now here R2 is a register name, but this is actually surrounded by a bracket. So if you see these kind of brackets, then you should immediately understand that these are in the indirect mode. And my destination, it is a register mode. So I'm asking you to move some data to R0, but let us see how to get the data operand here. Now, when I put R2 within a bracket, it says that R2 does not hold a data, it holds one address value. So we need to make use of that address value, go to that location and then get the data. So here is the processor and this is our main memory. So this denotes processor and this denotes main memory. Now, here in my processor, I have shown two registers. Here I am saying that R2 is one of the register. I need to see the content of R2. Now you can see it is not a data, it is an address value. I'll make use of this address value. I'll go to the main memory. Now this is the address location. I get to see the data here, that is 6. Now 6 will be moved to R0. See now here, that is why it is called as indirect. In case of direct mode or in case of register mode, directly the data was available in one step, but here it is two steps. First, I need to go to R2 and in R2, I will not get the data. I will get one more address value, use that address value, and then only you will get the data. So first, this is one, I have written it as X here, just to say that this is an hexadecimal number. So usually memory address will be in hexadecimal number. So then go to this particular location and the data is here, that is 6. That will be later on copied to R0. So after the successful execution of this instruction, R0 will hold the value 6. I have one more here, move, where I have written a memory location within the bracket. Here it was the register within the location, within the bracket. Here it is a memory location within the bracket. So first I need to go to that memory location that is called as B, where I'm going to get one more address location, that is 4000. Then I will go to that 4000 and X location. I get to see the data, that is 7 here, which I will copy into location called as A. So in case of indirect mode, we can either use a register or we can either use a memory location to hold the address. I think there is one doubt here. Let me see. Now see, in case of register and direct mode, I have written EA. EA stands for effective address as RI or EA as location. But here I made use of that register transfer notation, which is taught by Indu ma'am. Just to say that here effective address is nothing but the content of a register, or effective address can be a content of memory location. In the first one, my effective address I found as a content of one register. In the second one, I found the effective address in a memory location. So that is actually the name of EA. So the doubt is what is EA and RI in the register mode. Yes, EA means effective address. That means where do you see your data? In case of this register mode, RI, I have written it as I. That means I can write it as 0, 1 or 2 to n minus 1. So that I can be from 0 to n minus 1. If there are 32 registers in your computer system, it can run from R0 to 31. So that is why generally I have taken it as I here. Okay. And effective address here is nothing but where I find the data, that's the register. In case of this, I find the data in a memory location. That is why. So don't put the bracket here. Okay, because directly I get to see the data in the register. Here I directly get to see the data in a memory location. But whereas in case of the indirect addressing mode, effective address, that means address you are going to see as a content of one register, which you need to make use of to get a data. So put this bracket here to write the effective address of indirect. I'll continue. Any doubt? Actually, pointer, as all of us know, pointer will not hold any data variable. Pointer will hold the address of another location. So here is also, it is same. Now the next one is indexing mode. Indexing mode is also one mode which is used when you have to work with the arrays and when you have to work with a listed data structure. When you have a list of data items, then you have to use indexing mode. Now, till here already I taught you within the bracket means it is an indirect addressing mode. Outside, if you see any number, now this number I will call it as offset. So with indirect mode, if you are seeing an offset value, then immediately you have to think that it is an indexing mode. So here you can see, now I have used an indirect address mode. I have placed R1 within the bracket. that says that there is one register R1 in the processor, which will hold one more address. So I have used this bracket, and outside the bracket, I'm taking one offset value. Offset value here is 20. Now, if you are using the indirect mode along with an offset value, then the mode is called as indexing mode. And the register R1 will be called as index register. Now here I have taken add 20 to the content of R1, then only you get your effective address. So R1 is holding one address value called as 1000. So I just go to the memory location 1000 here, and then I know that there is an offset value 20 which needs to be added over there. So 1000 plus 20, it is 1020. So I need to go to the address location, that is 1020. There I will find my data operand, that is 6. So one addition to indirect mode is adding this offset value. That is only going to give you the final address. Now, as all of you had doubt a bit about effective address, see here. EA for this indexing mode, I'm writing it as offset plus the content of this RI. I didn't write it as R1. Those who are finding it tough, you can even write it as R1, but it can change. You can use any register, general purpose register here. So I'm writing it as generally as RI. So EA means the offset value plus the content of register. Now all of you go through this EA equation. So what I had done is like, I just saw what is the content in the R1, that is 1000. I just added this offset value. So 20 plus 1000, that gave me my effective address, that is 1020. So effective address is nothing but the address location where you will get your data operand. So that is 1020 here, where I got my data operand, that is 6. Now, there is one example also. It's in the next slide. In case of indexing mode, there are two small variations. Now, as I told you, this is called as index register. Now, you can sometimes take two registers also. In that case, one will be called as base register and one will be called as index register. So here I have taken two registers, that is RI, RJ. So to get my effective address, I need to add the content of RI with the content of RJ. That's a location where you can get your data operand. So R1, R3 also we can do. So this is one more variation of indexing mode. And sometimes along with the base and index register, we can even take a offset value also. That means X, Ri, Rj, something like 20, R1, R3. That means I need to add the content of R1, the content of R2, and I need to even add that offset value as we have done here. And then I get to see my effective address. Effective address is nothing but the final address where you will find your data operand. There was one address index. Okay. Students want me to explain the indirect mode once again. So indirect mode, as I've written the bracket only, I have said it acts like a pointer. That means first you go to one location, there you will not find your data, but you will find one address value, use that address value and then go to the memory to get the data. See here, first example, I have written it as move, and R2, I have used my source operand in the indirect mode. Now the source operand is in the indirect mode, destination operand is in the register mode. Now the difference is like the bracket always denotes indirect mode. That means first I need to go to R2. So the bracket says that R2 does not hold the data operand, it is a pointer, so it will be holding one address. So you can see that 2000 and X, it is a value of address location. Go to that location in your main memory of computer system. There you will get the value. So this is an indirect. Indirectly, you are going to get the data. Then the 6 will be moved to R0. See, first I moved to R2. I got one address location. Then only I got the data. There is a two-step process here. That is why it is called as indirect mode. Little extension to the indirect mode is adding one more offset value. Then only you get to see your effective address. Let me explain one program on index mode that will be clear. Now here I have taken the program which is there in your syllabus. Sometimes they ask you to write this program also in the exam. Now this is a program to add test 1 marks of n number of students and test 2 marks of n number of students and test 3, because we would like to find the performance of students in each test. So I need to find out 3 sum. Sum 1 is actually adding the test 1 marks of all the students. Sum 2 will be the test 2 marks of all n number of students are added, and test 3 of n number of students will be added and saved in sum 3. So I have first, now you see one new symbol here that is called as hash. Move hash of list to R0. Now this is in the register mode. Here we will see, now this looks like an immediate mode for us because there is a hash symbol also here. Whenever you use hash with a variable name, then the address of that particular location will be taken into consideration. Now I have already shown list. Now this is the memory. This is how your main memory look for this particular program. This is the program and this is how the main memory will look like. Now here is the list. Actually list holds the student's ID, the student's USN number or the roll number it will hold. Now this is the first student and that particular student's 3 test marks, IA1 marks, IA2 marks and IA3 marks. So 3 marks are here. Now this is the first student's USN number. Now I have said move hash of list. Now if I say hash, that means the address of this particular location needs to be moved to R0. Now I have written the address value also here. Address is nothing but 2000. So if I don't use hash here, then student ID would have been placed in R0. But I'm using hash. Hash denotes address value. That means 2000 will be moved to R0. Now onwards, R0 can be used as a pointer because R0 is not holding the value, it is holding the address. Then there are 3 instructions here: clear R1, clear R2, clear R3. Now, clear is an instruction in assembly language which just initialize the register with the 0 value. So usually before we save the sum or the result in one variable, we try to delete all the garbage value and have a 0 over there. That is the purpose. I have cleared R1, I have cleared R2 and I have cleared R3 because my intention is to use R1 to hold the sum of test 1 marks. R2 will be holding the sum of test 2, R3 then test 3. Then I will move n to R4. N is one variable where I will say how many number of students marks I would like to add. If there are 15 number of students in my class, then the value of n will be 50. I would like to add 50 students marks here. So that is actually the value of n. How many records? What is the size of the array? That is n here. So I have done all the initialization work here. I made R0 as a pointer because this is an example on indexing mode. So I need a pointer here. So I just took R0 as a pointer here, and R0's value is nothing but now 2000. 2000 is the address location of list where the USN number of student can be found. Now, initially it is 2000. So the 2000 is saved in R0. So R0 will act like a pointer. Now here is the branching concept, which you have already learned. I have taken one loop here. Initially, now the pointer R0 is pointing here. I have used index mode here. Add 4 of R0. Now this is in the index mode. This one, these two are denoting the index mode. Now this is the offset value and this is my index register. Now R0, as all of you know, R0 is right now pointing here. Now 4 of R0. I hope all of you remember that in this particular subject throughout we are maintaining our word length as 4 bytes. So it is word length 4 bytes. That means if this location is 2000, the next location will have address as 2004, next 2008, next 2012, so on. Every time we add 4 bytes. That's the word length of this particular computer system. It is considered as 4 bytes here. So the word length is 4 bytes. So this is 2000 now. When I add 4 to 2000, I know that my pointer will start pointing to the test 1 marks. So 4 offset value, I'm going to add to 2000. I'm going to get 2004, that is test 1 marks. So test 1 marks will be added to R1. Initially R1 was 0 here. Now first student test 1 mark will be added to the content of R1 and the sum will be saved again in the R1. There's a source and there's a destination. Same way, now I have not updated R0. R0 is still pointing here. I will move 8 offset from R0, that is 4 plus 4, 8. I get to see the test 2 mark of that particular student. I will add it to R2. Then once it is done, I will move 12 steps ahead of R0. I get to see this test 3 marks. I will add it to R3. But the pointer will be pointing here only to the first student USN number. Then I will make use of offset 4, 8, 12 and then try to get the test 1 marks, test 2 marks, test 3 marks. And I will save the sum in R1, R2, R3. Now one student test 1 marks is added. We have 49 more to be added. So what I do is like next time I make use of the immediate mode here. I add 16 to R0. R0 initially was 2000. Now when I add 16, the value becomes 2016. Now that is here. When I add 16, list plus 16, the pointer will come and start pointing to next student's ID number. That means one particular student's data we have already considered. Now let us start considering second student data. Now R0 will be pointing here. Now, as already you have out of this n number of student, one particular student mark is added. So let us decrement. Now, n value will be 49. So I do decrement R4. I keep repeating these steps, that's a branching, until I add all of them. That means until R4 becomes 0. That means no more students' records are left to be added. I keep on repeating this. This is called as branching. Same thing we taught in the branching. Now, whenever there is an example to be written for the branching, you can even write this example. So now all the students' records are added. Once it is added, you come out of the loop and move the final sum from R1 that will be in the register. As all of us know, register contents are temporary in nature. Copy it to the permanent location. Sum 1, sum 2, sum 3 will be holding the marks. So that was an example. There is one doubt message. What is the purpose of decrement is one doubt. There are two doubts I need to clear. First is actually what is the purpose of decrement? See, I said that in my class there are 50 students. So once the loop gets executed, I know that one student data is added. Now I have 49 students. Next time 48. So on I need to decrement. For example, whenever you write a for loop, how you write a for loop? For I is equal to, if you want to go like I is equal to 50, I greater than 0, I minus. The same thing I have done here. I know that there are 50 number of records I need to add it. Then first time once the loop gets executed, I have 49 more students record to be considered. Once again, once the loop is done, 48. So on, I need to keep on decrement once the loop gets executed until I add all of them. That means until the R4, which is used as a counter variable, reaches 0. See, R4 here acts as that I of your for loop. Okay. So either you have to increment or decrement. Here I am starting with the value of n, that is 50. So I keep on decrementing till I reach 0. That is the purpose. Why do we do decrement? Ma'am, please explain indexing mode. Indexing mode. I think that was in the previous slide where I said that there are variation of indexing mode. This is actually the one. I have written an instruction saying that add 30 R1, R2. Now here, this variation is actually for the base with the index as well as offset. Now you can see two registers here. One, I will say it as a base register. This is an index register. This is an offset value. So if R1 is 1000, maybe R2 would got a message saying that I'm not audible, but am I audible now? Okay, we cannot hear you properly. 2 minutes actually. Now is it fine? Audible? Not audible. So I'm just trying out in one more system. And now, am I audible? Yeah, okay. So I was explaining you the indexing mode example. So after the indexing mode, the next one is actually on relative addressing. In case of relative addressing, the register what we take is program counter. It is not a general purpose register, and we had taken in the index mode. So in case of index mode, I had taken an index register. That is one of the general purpose register of processor, like R1 or R2 or anything. But here in case of relative addressing mode, we take the program counter as an index address. Now you can see here, I hope you all remember that PC stands for program counter. And program counter is also a pointer. It holds always the address of next instruction. Now the offset value to be added to the address of next instruction. Now the relative addressing is the one which is actually used whenever there is a concept of branching. So as all of us know, we do branching either to a previous location or a forward location from the current place. So to the address of next instruction, you can add any offset value, then that will be used for branching. In your syllabus, there is no example on relative addressing because this is one addressing mode your processor will make use of whenever there is a concept of branching. So whenever you say that you would like to branch to another instruction, that particular distance that is called as an offset will be added to the content of program counter. As all of us know, program counter is the one which holds the address of the next instruction. Now, the last two addressing modes are the increment and the decrement one. It's written as an auto increment and auto decrement mode. Now here, instead of seeing an offset value, you will see some plus symbol, and in case of decrement, you will see a minus symbol. I'll just use one annotation. Give me 2 minutes. So Ri plus. In case of auto increment mode, first we need to get the content and then increment the pointer. That means it is especially used in case of arrays where I would like to read the first element and then increment my pointer to point to the next element. In case of auto decrement, first is the decrement and then only reading the content. Give me 2 minutes of time. There are some doubts in the chat box. Let me see that. Okay, let's see that. So already we have seen this example. I'll use one annotation. Now here, as I have told in the index mode, we will be using the general purpose register, but whereas in case of the relative mode, your processor would have used the program counter. Now let us see one example on the auto increment mode. This is something. And now here is an example on auto increment mode. Same example I have taken, which is adding of n numbers, which we have studied already in the branching. So same variables also I'll be using the registers as well as the n and all that. First, I will use the how many number of integers I want to add, that is in n, to R1. Then now you can again see here I'm using that hash symbol as I have used in the index mode. Now num1 is actually the first number. For example, if you want to add 1 plus 2 plus 3 plus 4 up to 10, your n value becomes 10 because you would like to add n number of integers, and num1 is 1. Now I would like to make use of pointer because I know that there is an array of integer. So first I want the R2 to be pointing to the first number, that is 1. And then it should be pointing to the next number, that is 2, 3, so on. So R2 first will be pointing to the first number. That is actually now R2 act as a pointer pointing to the first number. Then I clear an R0 just to save the sum here because the final sum will be saved in R0. To clear out the garbage value, I do clear R0. We'll start with one loop. Then here I am using auto increment mode. Now in case of auto increment mode, you will see one plus symbol after this indirect mode. That says that first you read the value. Now this is like an indirect address mode. As you know that R2 is holding one address value now, use that, get the content out, that is your first number, add it to R0, and then you increment the R2 so that R2 will be pointing to the next element. So as all of us already, as I have told, in case of auto increment mode, first getting the content and next incrementing the pointer so that the pointer will be pointing to the next element. So the first number is now already added to R0 and then the pointer will be pointing to the next element. Then as you know that out of 10 numbers, already one number you have added. Now decrement this counter variable. Now R1 is actually acting as a counter. Decrement that counter variable. Then now it will be 9 more integers to be added, and I know that that value is greater than 0. So I would like to again start with my loop, where again I read the second element first, add it to R0, then increment the pointer to point to the next element. So the second number from the array will be added to R0 now, and then the pointer will be pointing to the third number because it is an auto increment mode, reading first, then incrementing the pointer. So at the end of this particular loop, our second number is already added and your pointer will be pointing to the third number of your array. Now decrement the counter variable because already 2 numbers are added. Now R1 is 8. It is still greater than 0. So branch to 0 and continue with the iteration until you add all the 10 numbers. Now the final sum in R0, move it to a location called as sum. Now this is an example on increment mode. So all different types of addressing mode I have covered. There are 7 types. We have seen with the examples also. Next topic will be regarding input and output. So as all of us know now, the data has to be moved between the peripheral devices to our computer system. So we know that these peripheral devices, that is actually IO devices, are connected to our processor with the help of one bus. Now the processor and IO devices are connected to each other with the help of a bus. But we are also aware of that IO devices are slow in nature compared to our processor. Processor is very quick in execution, but IO devices are slow. So when I have to say that keyboard and processor, we know that keyboard is slow. The speed of keyboard is even depends on how fast you can type. So there is a speed difference between our IO devices and the speed of the processor. So we need some mechanism to synchronize. So I need a mechanism which can synchronize these speed difference. So whenever there is a speed difference, to smooth out the speed difference, we always introduce some buffers. So if there is one device which is slow in nature and if the second device is fast, then we have to introduce some buffer between them. So this is one first approach. Now the heading you can see as program controlled IO. In case of program controlled IO, the name only says you are going to write a small program which is going to control how the IO operation is performed. So here, whatever I said regarding the speed difference is written. As I have said, the solution is buffer. So now the buffers what we are going to use here are called as data in and data out. Hope all of you remember whenever we said different location like R1, R2, R3, I'm going for the register. A, B, C, I'm going to use for the memory. Data in and data out, we are going to use for the IO devices. So the buffers what we are using here are called as data in and data out. Let us see it with the diagram itself. Now I have taken here one input device along with the processor. The input device which I have taken is our keyboard itself. Now I have taken that buffer here, data in buffer. As all of you know, keyboard is slower than the processor. Now to smooth out this speed difference only, because the processor will go faster and the keyboard will be lagging. So we need some synchronization between them that we are going to achieve with the help of this buffer called as data in. And along with the data in this diagram, you're going to see one more small letter called as SIN. Here, S stands for status, in stands for in, because it's an input device, so it is called as status in. Now, this is a small bit, or it is called as flag. There are some doubts in the chat box. Let me see once. I just check the chat box and then continue. Okay. Okay. Now, so already I have said the meaning about SIN and data in. Here, these are the two program statements because of which this particular method is called as program controlled IO. Now here, I have written 2 lines of small pseudocode here. The read wait is actually one identifier what we are going to take. Now this, you can take any letters. You can even write it as RW, it's your wish. It is just an actually one identifier I'm taking. I have written one branching statement here. Branch to this particular read wait when SIN is 0. So whenever SIN value is 0, the control will be here only within this branching statement. Control will not go out. That means whenever you strike a key in the keyboard, it takes some time. And then this keyboard actually, whatever, if you type A, the A gets converted to ASCII value, and that valid ASCII value should be saved in the data in buffer. Once that valid ASCII value is available in the data in, then this SIN flag will be set to 1. So whenever there is a valid data available in the data in register, then only this SIN will be set to 1. Until then, processor will be waiting for the keyboard to complete. Okay, so when the keyboard is ready with the valid character, then that character from the data in will be copied to R1. Okay, so I'll just describe the diagram. So whenever the keyboard key is struck, the ASCII value gets saved in the data in register. That takes its own time here. It is slow, but the processor will be waiting. Once the character is ready, then the SIN flag, which can be either 1 or 0, will be set to 1. That tells the processor that now the keyboard is ready with the character. Then that character needs to be brought to the processor. So here the processor will be waiting for the keyboard to have a proper ASCII character. So this is how we can manage the speed difference between these peripheral devices and then the processor. Same thing, you have to write it for output devices also. In case of output device, the operation what you perform is writing. So write wait, branch to write wait only. That means you have to wait here only until and unless your output devices are ready. The minute output device is ready, this yes out will be set to 1, and then the processor starts outputting the character to the output device. So until and unless the output device is ready, the processor will be waiting here. Processor will be waiting for the yes out to be set to 1. Once yes out is ready, then the R1 will be copied to data out. So here, now this IO operation is entirely controlled by these two lines of small codes. So this is a very simple approach how your computer system can perform IO operation with the help of a loop. The same thing is written even using assembly language instruction here. Now before it was pseudocode, now here it is written using assembly language. The same loop I have taken here, read wait. It's an identifier, the name of the loop. You can take anything, any meaningful name like RW or read wait or anything you can take. I have used a new instruction here, new operator called as test bit. Now there are several such operators are available in your assembly language. We have already seen move, load, store, add. Now this is one test bit which does the comparison. And I'm comparing only the 3 bits of one register called as in status. Already I taught you data in, that's a buffer, SIN, that's a flag bit. Now this SIN, it's a small bit which is actually a part of this register called as in status. So in status is actually 8 bits long. Out of that 8 bits, the last 3 bits will be used for SIN. And if you see this as 0, as all of us know, we need to wait. Wait in just branch to read wait only. The minute it turns to 1, we will have to move the byte from the data into R0. Same thing which was in the pseudocode, we have written it in terms of assembly language. So any doubt, let me know. Now this is called as program controlled IO because small 3 lines of program will help us in doing IO between the peripheral device and the processor. So this is the first way of performing IO operation. Now, though it was very simple, it has many drawbacks. One of them is actually the wastage of clock cycle because the processor needs to wait in that particular loop for the IO devices to become ready, right? So those 2 wait loops, whatever we have used, where the time will be wasted. Why the processor has to wait for a slower device to complete? Can't the processor utilize that time for some useful task? So program controlled IO, though it is very simple in nature, it has this drawback. Solution to that is interrupt and direct memory access, which you will be studying in detail in the second module. So the next topic is stack. Okay, we were actually just solving the internet issue. As in between we faced some internet issue, it was little slow. So my voice also was not clear and the screen I was not able to share it properly. So now I think it is okay. So after the addressing mode, I started with the IO, where I just taught you one particular method that is called as program controlled IO. So from this module, the one possible question in your video question paper will be describe the program controlled IO. So where we just made use of some buffers and a status flag to smooth out the speed difference between the processor and the IO devices. So this entire method was by writing few lines of program. So though the approach was very simple, where the processor was waiting for a valid character in the data in register, the availability of valid character in the data in register will be denoted by the setting of SIN flag to 1. So once it is 1, the processor will read the data from the keyboard to the register. But it is very slow because the processor has to waste the time waiting in the loop. So, but we cannot waste processor time because performance will be always computed by how many work the processor completes in a time. So as we know, the solution is nothing but interrupts or direct memory access, which will be taught in the second module. So I will move on with the next topic that is called as stack. Stack you have already learned in data structure. It is the same data structure concept here also, but in CIVO we use stack as a temporary buffer. So stack is actually one temporary memory structure. So as all of us know, stack is nothing but a list of data elements, but there is an access restriction that elements can be added or removed only from the top of the stack. So always the top of the stack will be pointed by a pointer called as stack pointer. And as all of us know, the two operations which can be performed on stack are stack pop and stack push. So the one possible question in your question paper can be describe the stack operation. So here I have written the code for both the pop as well as the push operation. So in case of pop operation, as we know that we are going to read one element out of the stack. So to do so, always better to check whether your stack is empty. If your stack is empty, then you cannot perform a read operation. If the stack has some elements, then only you can perform a read operation. So I use compare statement. Now this is a stack which I am taking as an example. Now this is the bottom of the stack and this is the top of the stack. So that it is running from 2000 to 1500. So I compare whether the stack pointer is here at the 2000. If I see any value greater than 2000, like 2004 or 2008, then I know that the stack is empty. There are no element in the stack. I just have to say that empty error. You cannot perform reading operation because stack is empty. Else, I will make use of auto increment mode. As all of us know, if the stack is not empty, I would like to perform the reading operation, then increment the pointer so that it will be pointing to the next available item. So I make use of auto increment mode here and read the item out of stack and copy it in one variable called as item. You can use any variable name here. As we know that push operation is nothing but adding one element to the top of the stack. To add some element to the stack, first we need to check whether the stack is full. If the stack is already full, then we cannot add any new item into the stack. So this is the top of the stack, what I am taking as an example. So what I do is like I compare the stack pointer here. If I see that already stack has reached its top, I cannot add some more elements. So when I compare, if I see any value smaller than 1500, that means 1496 means already all the locations are occupied. In that case, I will just say that stack is full error. Then if not, I try to move that item which I want to copy into stack to the stack. To do so, the addressing mode what we have used here is auto decrement mode. In case of auto decrement mode, first the stack pointer will be decremented and it makes in place for the new element, and then the new element will be copied onto the stack. This is the same code what you have learned even in the data structure. It's the same stack and the same concept. But in case of your computer, stack will be used as a temporary buffer. Okay, this is also a one type of memory your computer makes use of, which is temporary in nature. So regarding stack, there is only one possible question in your question paper. So the next topic will be assembler directive. I think there is some doubt in the chat box. Reverse. One student is asking me, aren't these notation reversed? Yeah, actually here I have written greater than and less. Maybe if you compare it with the data structure, it may look like that I have reversed it. See, if you see your stack, what I have taken here as an example, it is going in the reverse direction. From 2000, then 1996, so on, it moves in the reverse direction. So whenever I have to do a adding value, then I will have to do decrement. When I pop out, then I have to increment. This is growing in the reverse direction. That is why it is looking like that. Maybe in the data structure, it was moving from 1500 to 2000. I have taken the same notation what is used in your computer system. In your computer system, the address can grow from a smaller value to the larger or from a larger to smaller. It depends on the specification. I followed the CO, our syllabus and the prescribed textbook. That is why I have considered that our stack is growing in the reverse direction. Or else, no, it can even grow from 1500 to 2000. In that case, it will be reversed. I have written this code by taking this stack as an example. So the next one more topic is on assembler directives. Now this one full question can be asked on describe assembler directives. Now, as all of us know, when you write program using assembly language, assembler is one software which converts that program into object program. Object program in the sense machine instructions. As all of us know, our computer understands only zeros and ones. It does not understand those mnemonics what we have used like add or move. It does not understand. It understands only zeros and ones. Now, assembler is a software which translates the program written in the assembly language to the machine language. Now, during this process, there are some directives which helps the assembler to do this translation. I have taken some of them. So the definition says directives are the assembler commands to the assembler concerning the program being assembled. So as already it is said, these are some of the directives. These are the directives which helps the assembler itself during the translation. There are 6 to 7 in your syllabus and their meaning I have written here. The first one, which is easiest one, is EQU. Now we cannot change this. These are the keywords. Now EQU just says that there is one variable and that variable is equal to some value. Now the use I have shown here, sum equal to 200. That means sum is actually a variable and the value is 200. Now the assembler, wherever there is a variable called as sum, it will replace that with the 200, the binary equivalent of 200. This is how the assembler directives will be used by the assembler. The next one is origin. As the name only says, origin means starting of something. Now here, it is nothing but the starting address of one data block. That means think that you are going to take one data block that is array only. You want that array to be started at a location called as 204. You are directing this to the assembler. Now what the assembler does is like, assembler will copy that particular array starting from a location 204. That's the origin of that particular data block. The next directive is data word. The data word actually says something like how many values. Now I have a data word with a n number of values. Okay. Then I know that when there are n number of values, for example, if I'm taking 100 integers, if I'm considering 4 bytes for every integer, I need to reserve 400 bytes of memory for that particular array. Okay, so reserve is only to reserve the memory, and just tells your assembler that your source code is already ended, the translation is already completed. Now the return, after once the entire translation is done, the control, whenever the control should go out of the current block, the return is actually the one directive which will be used. So these are few of the keywords which act as the directive to the assembler and helps the assembler during the translation of assembly program to machine language. So that was one small topic, one question you can expect from that. The next topic is very important. There are two possible questions from here that is called as subroutine. Subroutine, to say in general, it is like a function or it is like a procedure. Now, as we know that we write a function to perform a subtask. So subtask I can perform by writing a set of instructions. So subroutine is nothing but a subtask which consists of a set of instruction which is returned to perform that particular task. It is like our function what we have studied in the C program. Now I will explain the concept of subroutine with this particular diagram. The first topic here is called as subroutine linkage. The first possible question is describe subroutine linkage. Now, this is your main program here, and the subroutine what I have written is called as SUB. SUB is a subroutine which is being written here. This is a subroutine and this is my main program. So the main program was under the execution and we call the subroutine to perform a subtask, call sub. This is the name of the subroutine. Whenever a subroutine is called, control should go to that particular subroutine, which is also a set of instruction, and should start with the execution. Now here, when this particular instruction was under the execution, we get to know that the next instruction is at the location 1000. It should not be 2004. Basically, when 204, this particular instruction is under the execution, 204 will be the content of program counter, basically. Okay, but here at the 200th location, there is a function call. Then the next instruction which needs to be executed actually should be the 1000th location, not 204. Now it is time to change the content of PC from 204 to 1000. So that work is done by the call instruction. Now we will make use of one new register here that is called as link register. Previously, the content of PC was 204. Let us keep the backup in a new register called as link register. Then copy this new address where the execution should begin now to the PC. So this adjustment should be done. Now this is called as subroutine linkage. Once this is done, after 200, this 1000th instruction, this gets executed and all the rest of the instruction of that particular subroutine, once the entire subroutine is completed, there will be a statement called as return. As I have already told, return will take the control out of the current block. The return means I should come back wherever I have stopped in my main program, that is 204. So once the subroutine's execution is done, we will have to come back to this particular location and continue with the execution. That work is done by your return statement. That means the copy we had kept in the link register, that is 204, will be copied back to PC, and then once the subroutine is done, this next instruction will start with the execution. These steps and this diagram we will have to write for subroutine linkage. The explanation is here. Now this says what is the work of call statement and what is the work of return statement. So as all of us now know, whenever we actually branch into a function or a subroutine, we make use of this link register to take the backup of this particular address. But in your computer language, most of the language supports the concept of nesting. That means the main function can call add subroutine. Add can call one more function called as average. That means this nesting can be carried out to any depth. I may have 3 functions in my program. In that case, I have only one link register. Then where will I save those 2 return address? With only help of one link register, we will not be able to manage subroutine nesting. In case of subroutine nesting, when we have nesting of subroutine calls, we need all those return address in the last in first out order. And as all of us know, there is one data structure which works in last in first order is our stack. So when there is a large number of function calls in our program, let us make use of this stack. Now, if you call 2 functions in your program, let each function have its own workplace in a stack. I'll say this is a workspace of function 2. This is the workspace of function 1. And this is the area of stack. And each function will save all the local variables, whatever is required, and the return address and the parameters in its workspace. Now this makes the stack frame of function 2. And this makes the stack frame of function 1. So each function will have its own stack frame where all the local variables, parameter, and the return address will be saved. So whenever you call a function, the stack frame will be generated. Once the execution of that subroutine is done, this will be released. So that is a concept of nesting of subroutines where we need the help of stack. Now, you can see in this diagram, in addition to stack pointer, we are taking one more pointer called as frame pointer. Now you see the stack is large in size. So instead of making use of only one pointer, stack pointer, which also changes whenever you do push and pop operation, let us have one pointer for every function's stack frame. Now this much is for function 2, right? Let it have its own pointer and let us call that as a frame pointer. Let the function 1 has its own pointer called as frame pointer of function 1. To have a frame pointer in your assembly language, one should write these 2 lines. That is move frame pointer to the stack pointer and then make that frame pointer as a stack pointer of your stack frame. So these 2 lines should be written in our assembly language to have this kind of arrangements. So in case of subroutine, there are 2 expected questions. One can be describe the subroutine linkage method. The second possible question is nesting of subroutine. In case of nesting of subroutine, these 2 lines of code along with the explanation and this diagram needs to be written. Any doubt, put it in the chat box. I will start with the next topic that is called as additional instructions. In addition to those what we have already studied, there are some more instructions which are available in our assembly language are quoted as shift operations and rotate operation. In case of shift, you will find logical shift and arithmetic shift. In case of rotate, you will find rotate with the carry, rotate without carry. And I have written the direction also, whether you perform the shift towards right or left. But in case of arithmetic, you will find shifting towards the right direction. In case of rotation, you can carry out the rotation towards both the direction in both of these categories. So you have these different types of shift and rotate in your syllabus. I have explained it with an example. Now this is a logical shift towards left direction. Whenever you move one position towards the left direction, this one will come here, this one goes here. So on you will have to shift the bits towards left direction, one place at a time. As you know that when you shift, this place will be vacant, add it with the 0. If it is a logical shift, add the vacant place with the 0. But this one which goes out, for some time it will be saved in the carry flag, then it just gets discarded. This is the shifting, just shifting one place towards the left direction. Same way, you can even perform logical right shift, shifting the bits towards the right direction. The vacant place will be generated at the most significant bit place, will be added with a 0, and this one will be discarded. I have taken the same example, which is there in our syllabus. Now, this is the content of R initially. Now, L shift L is the operator. L stands for logical. This L stands for left. In case of right direction, logical shift right is the operator name. Now, these are the content of register. Here you see, we have asked you to perform the shift 2 number of times, not just once, it is 2 number of times. This is the original content. Perform the shift towards the left direction. When I do it once, this one will come here, this one, so on I shift, this 0 goes out and gets saved here in the carry place. When I do the shifting twice, you know that these zeros and ones will be discarded. This one is here, you can see, this one is here, this 0 is here. So on here, there will be 2 vacant place which gets generated, will be added with the zeros. It is nothing but shifting towards a specified direction, specified number of times, add 0 to the vacant place, and whatever is going out from here, discard it. That is just the logical shift. Same thing we have even shown here for the right direction. When I move the entire content to the right direction, the vacant place will be generated towards this direction, will be added with the 0, and these 2 ones, when I shift it towards the right, will be discarded. So this is all about the logical shift. We have arithmetic shift, one more category. In case of arithmetic shift, in our syllabus, only towards the right direction is added. Now, when I perform the shift towards the right direction, basically it is towards this direction we move, and the vacant place we fill with the zeros. But if it is an arithmetic shift, don't just fill it with a 0, fill it with a sign bit. I hope all of you remember the most significant bit. If it is 1, we consider our number as negative. If it is 0, we consider our number as positive. So here you can see my number, whatever I have taken in R is a negative number. So when you shift it towards this direction, if it was logical, I would have added zeros here. But I am now performing arithmetic shift operation. So see, I repeated the sign bit. The vacant place, I will add it with the sign bit. That's the difference between logical and arithmetic shift. Arithmetic shift in only right direction is added in our syllabus. Any doubt, you feel free to put it in the chat box. Now, after that, we have something called as rotate operation. As you can see that in the shift operation, the bits which goes out of the register will be discarded. But that is not the case in case of rotate operation. In case of rotate operation, there are 2. One is towards the left and right, but with the carry, without the carries are the categories. This diagram, this is the diagram where your rotation operation is without considering the carry. This is for when you consider with the carry. Initially, these are the content of register. When I rotate, this 0 will come and take the carry register. This 1 will come here. Then don't put 0 here directly. Whatever goes out of the register, now here it is 0, add it towards this end, vacant place, not like our shift. Here whatever bit which goes out will fill the vacant place. But the carry will not be considered because it is without the carry. For the next step, this 1 will come here and this 1 will be rotated out of the register, will come and occupy this place. And the carry, whatever goes out, will take this place. But see with the carry. First rotation when I perform, this 0 comes here, this 1 will come here, and the 0 occupies the least significant place. For the next rotate operation, you have to consider this one, whatever was there in the carry, that will fill the vacant place. Now see the arrow mark and perform the rotation in the same direction. Then it will be easier for us. Remember the diagrams, then it will be easier for it to do with the sum. Now both of this is the final content after to rotate operation. Now that was the rotation with as well as without the carry. Any doubts, you put it in the chat box. I'm going little fast because we have one more module to be covered. The last topic of this particular module is encoding of machine instruction. This is the last topic from module 1. In case of encoding, as all of us know, once your instructions are brought from the memory to the processor, before it gets executed, it needs to be converted to a binary format, zeros and ones. Now that is called as encoded instruction. An instruction which is in the binary format is called as encoded instruction. The assembler is the one which does that work. Now, whenever you take one operation, for example, add, move or anything, every operator will have one opcode. Opcode means one binary number associated with that particular operation. So opcode, your source operand, your destination operand, and any other information. Generally, as I have already told, 32-bit, that means 4 byte, will be the word length of our computer system. Out of that, let us at least reserve 8-bit for the opcode. 8-bit means I can perform 2 to the power 8, 256 operations. 256 different operations I can able to manage with the 8-bit. Then think that my computer system has only 16 general purpose register. Then I need 4 bits. 2 to the power 4 is 16. So I need with the 4 bits, I can give each register a unique name. Then, as all of us know, there are 7 to 8 different types of addressing mode we have studied. To say which addressing mode we are using, I need 2 to the power 3, 8. That is 3 bits. Now, for an instruction like add R1, R2, 8 bits I will reserve for this add, that's opcode. 4 bit to name R1, 3 bits just to say that this is a register addressing mode. Same way for the R2, 4 bits I'm using for the register and 3 bits to just to say that I have used register mode. So this much of place, 8 plus 4 plus 3 plus, this value is 22. As I know that my one word is 32-bit long. So 32 minus 22, I'm left only with the 10 bits. I'm left only with the 10 bits, which I can make use of for any other additional operation. Now, for this, it was small instruction, it is fine. But guess that you have a large instruction where you made use of one memory location, like location. In that case, only 10 bits will not be sufficient for you. 2 to the power 10, that is 1024 or something, will not be the size of your main memory. Main memory is large. So only 10 bits will not be sufficient for me. In that case, I may need more than one word to accommodate an encoded instruction. So encoded instruction may take more than one word. Okay, one word will not be sufficient. Now, in the olden days, there were some systems where only instruction could take one word of size. It could never make use of more than one word. Such computer systems are called as RISC system, reduced instruction set computer. But nowadays we find systems where our instructions after encoding can take more than one word. Such systems will be called as CIS system, that's a complex instruction set computers. Now for the encoding, you will have to mention these 2 slides in your exam. That actually completes the entire syllabus of module 1. All the topics from the module 1 are over. Now, actually, I'll have to hand over the session to Salangai ma'am. Salangai ma'am, Professor Salangai ma'am will continue with the second module, that is on IO organization. There is one doubt saying that repeating the shift operation. That's a very easy operation. As the name only says, bit by bit, we will have to shift either towards the left or towards the right direction. So in case of logical shift, now this is for the left direction. When you move One by one, you try to move it towards the left directions. In the sense, you will have to shift it towards this direction. This is the original content. You are asked to shift it twice. Logical, L. This one, let it come here. This one, you just move it towards the left direction, one place. In that case, naturally, you will be having one vacant place here. Add 1 0 over there. Wherever there is a vacant place, you will have to add a 0. And this 0, after one shift, will be moved out. Discard it, don't consider it. Next time, move once again so that you get two vacant place you would have got, because you have to move towards left direction two number of times. You would have got these two places. Add zeros over there. Two zeros were added. And when I move twice, this one and this 0 will be discarded. You will get your content as 1 1 0, then the rest of them 0 1 1 0 0. That is how is the content of this register is generated. This you can practice seeing these diagrams only. These diagrams are very self-explanatory in nature. That is why. So I thank all of you. Now I will hand over the session to Professor Salagai ma'am. She will start with the second module. Yeah, she will take a break of 5 minutes and then she will continue with the content.
Good afternoon, everyone. So from morning, you people are discussing about the module 1, and you have cleared with the basic concepts like addressing modes and how the data has been stored in the registers like data in and data out, and how you are going to access the input output devices. Okay, so we have a brief introduction in the module 1. So now we are going to check with the module 2, that is input output organization. Okay, so as the name itself tells that, so how we are going to organize the input output devices. Okay, so if the organization means, so what we are going to do means, so we know that we have a system and we have a lot of input output devices connected to the computer, and how we are going to access those devices. Okay, so if the processor wants to display some data to the users, it have to access the output devices like monitor. And if the processor wants to get the input from the user, it will use the input devices like keyboard or mouse, or we have a number of input output devices. Okay, so using those devices, we are getting the input from the user and we are displaying the data to the user. Okay, how we are going to organize this input output devices? So mainly, so if you want to access the input output devices, we have two mechanisms. Okay, so first is, so when we are going to study about the input output devices, we know that each and every input output devices will have a unique address. Okay, so this address will be stored in the memory. So how we are going to share the memory with the address space within the memory, or we are going to give the separate address space for the input output devices. Okay, so that's the first thing. So when you're accessing the input output devices, so first we will have this is a basic this is the basic diagram where we have a processor and memory, so which is connected to a processor bus, and we have n number of devices which is connected to the processor bus. Okay, so each and every, as I said you before, each have a unique address, and this address needs to be stored in the memory. So before accessing these devices, so you need a specific address that to be retrieved from the memory, and you have to give it to the address line, and the device want to recognize the address, and if it get matches with the address, it will reply back to the processor. Okay, so when you're storing the address of these devices, we are going to store it in a memory, or we are going to give a different space or a unique space for storing your input output device address. Okay, so next we'll have, one second. So as I told you that you have a way of accessing the devices. The first one is memory mapped input output. So as I told you before, so the input output devices and the memory share the same address space. We are calling this arrangement as memory mapped input output. And here they have given you the example. This kind of instruction you have seen in the module 1. So you are trying to move the information which resides in data in to the register RO. There is a first instruction which has given here, that is move data in to the RO, and you have a move R0 to data out. Okay, so if this kind of instruction will be executed by the processor, so how the instruction, that is this instructions need to be access your memory, because it needs to take the data and it have to take the data from the data in, and it have to access the register R0, and it have to save the content or copy the content to R0. And in the second instruction, whatever data which resides in R0 I have to be stored back to your data out. Okay, so in your memory mapped input output, so we'll be having a special instructions. We have an instruction like move, and we will be having data in R0 registers we are using, and we are going to perform your memory mapped input output. So this requires this kind of access. It doesn't require a special instruction, and it is slow when compared to your input output mapped input output, IO mapped IO. So the IO mapped IO, that is the unique space will be given to store your input output device address, and you doesn't have, that is, it is not going to share with the memory. And next is your interface. Okay, so these things you have studied in the first module. So what is interface? So the interface is nothing but the hardware which is used to connect your output device to the processor. So if you want a peripheral, if you have a peripheral devices, so this peripheral devices will be connected to a processor or any component of your system using this interface. So in this input output interface, you will be having three major components like address decoder, and you have a control circuits, and you have a data and status registers. So what is the use of address decoder? So the address decoder will decode the address. Okay, we know that the all the peripheral devices have its unique address. So when the processor sends its response to get which device has need an access, so it can be done by your address decoder. The address decoder will the address decoder will decode the address, and next you will be having a data and status registers. So we know that what is the use of data and status register. So the data register, which is used to hold the data, and the status registers, we know we have two status registers, S in, S out. So the S in will be set when you have an input from your when you have a data from your input device, and S out will be set to 1 when you have a data to be given to your output devices. And we know that the control circuits will be helped for controlling these address decoding and data and status registers. So all the devices will be connected to your processor using your input output interface. So next is, so actually this module 2 will have a concept of these three mechanisms. The first is a program control input output, and next is your interrupt, and next is a direct memory access. Okay, so this is the three mechanism we are going to study in detail about we are going to study in detail the module 2. So in the program control, so this is the concept which we have been discussed in the module 1 itself. So in the program control input output, what the processor normally does is, it's the processor will be keep on checking the status registers of your peripheral devices. Okay, so we have heard about a data in and data out, or the two registers which is used to store the data which have been got from an input device, and if you want to transfer the data to the output devices, it will be get stored in the data out. Okay, so what happens in the first mechanism, programmed control input output? So the processor have to keep on check these registers, so periodically. So it have to check for example, once after 5 seconds or once after 5 nanoseconds, it have to keep on checking these registers whether the data has been available in these devices or not. So what happens when the processor will get wasted, and instead of the processor time to be checked these register, because whether the data has been available or not, we are making the processor to work on it. Okay, so this is a main drawback we have in the program control input output. Okay, so to overcome the drawback of program control IO, so they have been introduced a mechanisms called interrupt. So what happens in the interrupt? So mainly when the device is ready. Okay, so if any of your devices, for example, if the keyboard you are pressing a key, that is you have given a keystroke, and the data, whatever key you have pressed, the data will be get stored in the data in registers. Okay, so once the data has been available in your data in register, we know that this SN register will be set to 1, and we are not making the processor to check your SN because we are using a mechanism called interrupt. So what the device will do means, so whenever the data is available, the device will generate a signal, and it will intimate the processor there is some data is there in the register and it requires your attention. Okay, so this is interrupt is nothing but you're disturbing the normal process, and you're making the processor to pay your attention for those devices. Okay, that is the interrupt. The next mechanism is your direct memory access. It is DMA. So this direct memory access, which will be used mainly for high-speed input-output devices. That is, if you want to transfer a bulk of data. So this kind of direct memory access will be used. We are going to discuss in detail about direct memory access in the upcoming slides. So now we will discuss what is programmed control input output. Okay, so as I told you before, there is every input output devices will operate at the different speeds. Okay, so the speed of the processor will be varies with the peripheral device speeds, because the process speed will be more and these devices will be little slow. So to overcome these things, okay, so we are going for this kind of, that is, we have to overcome the main drawback, we have gone for an interrupt. Okay, so now just next we will study about what is interrupt and what is ISR and other things. Okay, so as I told you that what is interrupt, just interrupt is nothing but, so when the processor is ready, it is going to send a hardware signal, and it is going to, that hardware signal we are calling it as an interrupt. Okay, so why we have gone for the interrupts here, we know that there is a problem, there is a drawback in program controlled input output. So to overcome the drawback, we have come for the interrupt concepts. Okay, so mainly when the interrupt occurs, okay, so what we know that the interrupt is nothing but a hardware signal which you have been sent to the processor and intimating the processor that it requires, that is, the devices requires its attention. So how the processor is going to handle the interrupt? Okay, so for each and every interrupt, there is a specific set of instruction which has been coded and it have been stored already. Okay, so the set of instruction, you are calling it as a interrupt service routine. So what is interrupt service routine in the sense? See, for example, if any process is disturbing your normal flow, so the processor have to decide what kind of action needs to be taken to carry out this process, because the processor is executing some set of program. So when you're executing a program, in the mid of the execution, the interrupt has been happened, and the processor pays the attention to the interrupt, and it have to decide what action need to be taken. So this actions, the set of this actions will be written in a form of instruction, and it will be stored it in ISR. That is the interrupt service routine. So interrupt service routine is nothing but a set of instruction which will be stored for each and every interrupt. Okay, and mainly if it comes to the interrupt service routine, so the first and last line of this particular ISR is very important. The first line of your ISR, that line, that is, it is a core set of instruction line. The first instructions will be your enabling, that is disabling your interrupt. Okay, so what is disabling the interrupt? Why this specific line has been set as a first line of your interrupt service routine, in the sense, so when a particular device initiate your interrupt and the processor is executing the interrupt, okay, so you should make other devices, for example, you will be having n number of devices connected to your system. If the device input output device 1 initiated your interrupt, what the processor have to do, it have to pay attention to the device 1. And if at the same time, if the processor 2, if the device 2 initiate your interrupt, so how the processor will handle the situation? So to overcome it, what it does is, so it will make a line as disabling the interrupt. So disabling the interrupt will make the other devices not to generate an interrupt. The other devices will be kept quiet and it will not generate an interrupt, and it will be make the processor to handle the first particular interrupt, and once it get released, the other devices have a chance of generating the interrupt and get the processor attention. So the first is disabling the interrupt, and next is after disabling the interrupt, so you have a set of instructions followed to handle that interrupt. You will be having an ISR. So the ISR will be having in disabling the interrupt and a set of instruction. The last line will be enabling the interrupt. So once you have been executed all the instructions, so whatever actions required, if it is taken it, and last you have to enable all the interrupts. So as I told you, so you have enabling and disabling interrupt in the ISR, and this is the how you are going to transfer the controls. Okay, so this is the example they have been given you. You have a user program here. So you have a user program. So the user program has a set of instruction. The instructions will be start from the instruction 1 to instruction M. So when the processor is executing the instruction I, okay, so the next instruction have to be executed as I plus 1. Okay, so when the processor is executing the instruction I, so the processor receives an interrupt from a device, and the processor holds the execution. That is, this is the normal execution which was carried by the processor. So when the interrupt has been generated, what the processor have to do? The processor have to hold on the normal execution, and it have to execute the ISR for the particular interrupt. So the instruction execution, that is which instruction is executing here, the instruction I is executing here, it gets stopped, and the control is being transferred to your ISR. So this ISR is nothing but the interrupt handler. So how you are going to handle the interrupt? Either by executing the interrupt service routine, you are going to handle the interrupt. Okay, so the interrupt handler, that is the ISR, when you're executing the instruction, when you're executing the instruction in ISR, we know that the first instruction of the ISR is your disabling the interrupt, and after it's followed by your set of instructions. That is, if you're getting an interrupt from the keyboard, so what is the set of actions, what are the set of instruction will be resides in the ISR? So with the keyboard, the key has been pressed, and the data will be get stored in data in. Okay, and what after storing the data in, SIN will be set. Okay, so you have the processor have to check the status flag, that is SIN, and it have to take the data from your data in, and it have to give it to the processor for computation. So this is the action have to be taken for the particular interrupt which generated by the keyboard. So this action will be written as a set of instruction, and it will be stored in an interrupt service routine. And before executing these instructions, so we know that the first and foremost line which have to be included in your interrupt service routine is disabling the interrupt. Okay, so after disabling the interrupt, it will make other devices not to generate the interrupt, and after executing the action required for the keystroke which you have been pressed using the keyboard, and after performing the action, you have to enable the interrupt back. Okay, so this is the interrupt handler. So once you have executed all the instructions here, the control will be transferred to the instruction. So where it have to come back? It have to come back to the instruction I plus 1. It have to come back to the instruction I plus 1. And this is the instruction which have to be executed by the processor, because before starting your interrupt, the instruction I has been completed execution, and the next instruction which is supposed to be executed is I plus 1. So after executing the ISR, the control will be come back to the I plus 1. And if you see the diagram, it is look like a subroutine call, right? So if you have a subroutine in your program, what it does, you will be having a subroutine followed by a subroutine name. So when the processor have this kind of instruction, what the processor will do, the processor will transfer the control to your subroutine, and the subroutine, you know that it is a collection of instruction. So the repeated, so if you don't want to repeat the instruction in your program, so those repeated instruction will be stored in a subroutine call. Okay, so the subroutine will be executed, and it will be come back to the previous location. So we know that. So we know that how this address and all will be stored. So because the program counter which holds the address of the next instruction. So because I plus 1 is the next instruction which have to be executed. So this program counter address, you have to be changed to the interrupt service routine first instruction. So what is the address of the first instruction of the ISR will be replaced by your I plus 1. And this after control will be shifted to a normal execution, right? Again, this I plus 1 have to be restored back from your link registers, because the link register, program counter, what will be reside in the program counter, what is the use of link register. So all those things we have been discussed in the module 1. Okay, so what I'm coming to tell here is, so when you're transferring the control from a normal execution to handle the interrupt, it is also looks like a subroutine call. You have to transfer the control to ISR, execute the instruction, then come back to your normal execution. Okay, so next, after I have given an introduction of what is interrupt, how the interrupt will be handled, and what is ISR, what is the first and last line of your interrupt service routine, I have told you. So next is how you are going to handle the interrupt, whether we need any hardwares to handle the interrupt, and how this interrupt hardware has been designed to handle the interrupt by your processor. Okay, so this is a block, this is a diagram. So you can see here, so these the first, that is INTR1, INTR2, or nothing but your input output devices. If a device 1 initiate your interrupt request 1, that is INTR1 and INTR2, this is the interrupt request line for the device 2. So if the device wants to initiate an interrupt, so it will be done by closing the switch. Okay, so this is the switch. So this is the switch. If the switch gets closes, which means that the device 1 which initiated an interrupt called interrupt request 1. Okay, so likewise we will be having an switch mechanisms in all the devices. If the device wants to initiate an interrupt, it will be done by closing the switch. Okay, so next you can see that is a resistor, that is a pull-up resistor here, and we will be having an VDD. So this is a voltage supply which will be supplied permanently for your all the devices. Okay, so it will be inactive. So this voltage will be inactive initially. So when the device wants to initiate the request, so the switch will get closed and the device will initiate the request. It will reach the processor and the processor will execute your interrupt service routine, and it will make the other devices by executing the instruction disabling the interrupt. And once the instruction presents in the ISR executes, you are going to enable the interrupt. Okay, so next is we will be having a few, that is we will be getting some questions. So there is a chance of how the processor is going to recognize the device when the device is requesting an interrupt. Okay, so how the processor knows that this is the particular device which requests for an interrupt. And we will be having a few more questions. That is, how if your interrupt has been generated, we know that ISR is going to execute, how the address of the ISR will be obtained by the processor. This is the next question. And after that, we'll be having when one device is initiate the interrupt. Okay, so whether the processor can able to process the other interrupt, and we can, whether the devices will be can generate a simultaneous interrupt, how the simultaneous interrupts can be handled. Okay, these are all the questions we have of based on the interrupt. And we are going to find out how the processor is going to recognize the interrupt and how it is going to identify your interrupt service routine address. It is each and every routine will be started with an address, right? So how the address will be identified, and whether the processor has a capacity of processing the interrupts of multiple devices, how the simultaneous interrupt can be handled. Okay, so now to handle your multiple interrupts, the first question. So what is the first question we have saw in the previous slide? So how the processor, how the interrupt service routine address will be. So how we are going to identify your ISR address. Okay, were you all three? Okay. So vector, the next one is the vectored interrupt. So what is vectored interrupt is? So when the device is requesting an interrupt, okay, so it is going to identify itself by sending a special code to the processor. Okay, so this special code which contains the address of your ISR. Okay, so what is the question we have discussed in the previous slide? So how the processor is going to identify the address of your ISR. Okay, so when the device is requesting for the interrupt, what it does means, so actually when it is requesting, it will send a special code along with the request. So the special code is nothing but your address of your ISR. Okay, so this special code is nothing but a 4 to 8 bits which will be sent along with your input output, that is interrupt request. One second. It will be sent along with your interrupt request, and the processor will process the request, and it will find the ISR and it will execute the ISR. Okay, so next is interrupt nesting. So in the interrupt nesting, see here, see actually in the block diagram, you have a processor and you have a n number of devices connected to it. For example, from a device 1 to a device n. So each and every devices will be having a separate line, that is interrupt request line and interrupt acknowledgement line. Okay, so why we have gone for an interrupt nesting? So this interrupt nesting will provide you the answer whether whether more than one device can generate an interrupt. Yeah, more than one device can generate an interrupt, and how the processor is going to address this problem. Okay, so the processor is going to address this problem by giving a priority to all the devices. For example, the device 1 which carries the priority 3 and device 2 which carries the priority 1, and the device 3 will be carrying the priority 2. Okay, so each and every devices will be having a different priority structure, and based on the priority the processor is going to process the interrupt. Okay, so n number of device, more than one device can generate an interrupt, and the interrupt can be handled by the processor by checking the priority level of the device. So if a device 1 and device 2 issue a simultaneous, that is, it has been, both have been requested for an interrupt simultaneously. Okay, so it has generated the interrupt at the same time. So when it generated an interrupt same time, the processor will check for the priority. If the device 2 has an higher priority when compared to device 1, okay, the processor, what it does, it gives a chance to a device 2, and after once the device 2 request is processed, the device 1 will get a chance to process its interrupt. So that's why we will be having a separate interrupt request line and interrupt acknowledgement line. So the interrupt request line, if the device want to generate an interrupt, it can have a unique, it can have a separate interrupt request line and interrupt acknowledgement. It don't want it, it will not wait for a common interrupt request line and interrupt acknowledgement line. So come to this acknowledgement, why we need the interrupt acknowledgement line. Okay, so we know that, so if the device is generate an interrupt, because this device doesn't know that whether the processor receives its request or not. So once the processor receives a request from any of the device, so once the processor receives an interrupt from any of the device, what the processor has to do means, so immediately it have to issue the interrupt acknowledgement and telling the device to wait for its response, because this acknowledgement will tells you that the signal you have been generated and pass it to the processor, it has been received and the processor is going to address you soon. Okay, so this is the use of interrupt acknowledgement. So next is to handle the problem of a simultaneous request. So we have the combination structures. So one is your daisy chain mechanisms. So to handle your simultaneous request, so in your daisy chain mechanisms, what you have means, see, you have a series of devices, that is device 1 to device n we have, and we have a common interrupt request line, and this common interrupt request line will be used by all the devices to carry the interrupt request line. When the process issues the interrupt acknowledgement, it will be sent and it will go through all the devices. So if the device 2 issued your interrupt, okay, it has used the interrupt request line and it is issued your interrupt request, and the interrupt acknowledgement has been sent by the processor, it will comes to the device 1. The device 1 will check for the information. If it doesn't initiated a request in an interrupt request, it will make the acknowledgement to pass through the device 1 and it will reach the device 2. Okay, so this is the daisy chain mechanism. So to handle your simultaneous request, so what we have been done is we have provided a combination of your daisy chain and the priority structures. So in your interrupt nesting, so I have told you that we are issuing the priority for all the devices. So depends on the priority, the processor is going to handle the interrupt. Okay, so if the priority level is higher, the device which have the higher priority will get an access, and the device which have the lower priority will have to wait until the higher priority devices process it, until the higher priority devices request has been processed. Okay, so this is the arrangement where you have a combination of daisy chain and a priority structure. So in the daisy chain, what you have, see here, you will be having an interrupt acknowledgement line which can be passed through all the devices. So if the device 1 initiated an interrupt, it will initiated an interrupt. What it does, it will acquire this interrupt acknowledgement and it will not make the acknowledgement to pass through the other devices. Okay, and if in the priority structure, so each and every devices in this particular line, that is, this is the first priority where you have a first device 1, device 2, and device n. This is the first priority group, and then this is the next priority group. So in this group, you will be having a different priorities, and it will be connected in a daisy chain mechanism. Okay, so this is a way to handle your simultaneous request. And next is controlling your device request. Okay, so hope you have been cleared with the interrupts concept. That is interrupt, what are the things we have been discussed in your interrupt. So what is interrupt, what is interrupt service routine, and how you are going to enable and disable the interrupt, and how you are going to handle the multiple request by using polling scheme, vector scheme, and we have a daisy chain, and we have a priority. That is the combination of priority and daisy chain we have been seen to handle the simultaneous request. Okay, so next is how you are going to control your device request. So here we have, and apart from your interrupt concept, that is, we know that we have a polling scheme. So what is a polling scheme does? So the processor have to keep on checking your bit, that is, it have to keep on checking the bit like interrupt enable bit and interrupt disable bit. So if the device wants to initiate an interrupt, it have to set the interrupt enable bit to 1. Okay, and if you don't want the device to generate an interrupt, you have to make the interrupt disable bit to 1. Okay, so this is the way to control your device request by enabling and disabling your interrupt bit, which is there in your state. That is, there we have a different kind of flags registers, right? So using the flag registers, you can set the bit and you can make it enable and disable. So next is the exception. So what is the use of discussing this exception is, so interrupt is also a kind of exception. So exception is means what? So you are disturbing the normal flow, and you are going to make you are making the processor to provide the attention to the particular problem. Okay, so we have a various kinds of exceptions. So the kinds of exception is, first is we have a first exception like a recovery from errors. Okay, so in the recovery from errors, so when the processor is executing an instruction, so if the particular instruction is wrong, or if you doesn't have a proper syntax, or the variables has been not assigned properly, and it doesn't have enough data to execute the instructions, so there is a chance of getting errors. Okay, so this is the one kind of exceptions we have, and we have a debugging. One of the next kind of exception is a debugging. So in the debugging, which will be used by the programmer. Okay, so debugging will be having a two things, that is a tracing and a breakpoint. So in the tracing, so what you have is, the tracing is nothing but if I want to trace what happens when I'm executing each and every instructions. Okay, so that is called tracing. So if you're executing one instruction, there is a possibility of values will be get changed in the memory, and you will be having a different changes. You will be having a various changes when you're executing an instruction. Okay, so that can be traced by the programmer using a concept called tracing. Okay, so tracing is nothing but you're going to identify what happens when you're executing each and every instructions. So next is breakpoint. So what does breakpoint mean? It is a user specific point you have been set in your program. So you are going to specifically tell after execution of this instruction, what happens, what kind of changes it has been happens in the memory, and what output we got. So which can be set by using the breakpoint. Next is the privilege exceptions. So in the privileged exception, so we know that you can be the instruction can be executed in two mode. That is the user mode, and you have an supervisor mode. Okay, so the user mode doesn't have all the rights to execute the instruction. You will be having a various kind of instructions which will be executed only in your supervisor mode. So those instructions can't be executed in the user mode. Okay, so when you are trying to execute the instruction which can be executed in the supervisor mode, the exception will be arised is called privileged exceptions. So you have a privileged instruction. So those privileged instruction can or trying to be executed in the user mode, the exception arises is called privileged exceptions. Okay. So next is the direct memory access. So far I have told you that the module 2 will be running around with this three concepts, that is programmed controlled input output, and next is interrupt, and next is a direct memory access. So in the direct memory access, I have told you that, so this is the mechanism which will be used for transferring the data at the if you want to transfer a bulk of data. So if the input output devices want high speed of transmission, so we were using access called DMA or direct memory access. Okay, so here in the DMA procedure, so what the processor have to do is, I will tell you that what is a DMA. That is, the name tells you that it is a direct memory access. So here, without the processor involvement, we are trying to access the memory. That is, the input output device is trying to access the memory without the involvement of processor. Okay, so the processor is not going to help you in retrieving the data or storing the data. Without the involvement of processor, you are going to execute all kind of process, that is reading, writing, that is what you are trying to execute all kind of operation. So that is called direct memory access. But we will be getting a question, so how without the processor involvement, so how this read operation and write operation between the processor and input output device takes place. So first, before handing over this operation to your DMA controller, the processor will tells you that where you have to start the address. For example, you take the processor wants to read an 4 bytes of information from your memory. Okay, so if the processor wants to retrieve the information, you don't want to take a processor. Just because we are taking without the intervention of processor, we will take a different examples. Like, so the output devices, the input devices data has been given and it have to store it in your memory. Okay, so if you want to store the data in your memory, you need an address where the particular information have to be stored, which address it have to be stored, and how long the information have to be stored it, and what is the starting address, and what is the word count, and what kind of direction it is, whether it is an memory to the device or device to the memory. Okay, so this kind of information will be given by the processor initially, and it will be, this kind of information will be handed over to a controller called a DMA controller, and based on these information provided by the processor, the processor will hand over this information to the DMA controller, and the DMA controller will check for the information and it will proceed accordingly. So this is the DMA registers looks like. So you will be having a request, interrupt request bit and interrupt enable bit. And what are the information you have in your you have in the DMA? So like you have a starting address and the word count and the direction of your transaction. That is direction of your transfer, whether it is from to the memory to the device or device to the memory. Okay, so this is the block diagram of DMA controllers. See here, you will be having a processor, you will have a memory, and you have a DMA controller. So the DMA controller will take the information from the processor, and without the processor intervention, so it is going to access the input output devices. If it want to transfer the data from your processor to your output devices, the processor will hand over the information to the DMA controller, like starting address and word count. The DMA controller will get the information and it will provide the information to the processor. That is whether you have to give the data to your output device, or whether you have to get the data from your input devices, it will. Okay. So next is memory access. Okay, so when you're going to do memory access, so you have an So how you are going to access the memory? Okay, so memory access will be done by the processor, and you have a DMA control which helps you to handle this transaction. And when you have a DMA device, it is if you have an input-output devices, so when the DMA device is initiating an interrupt, the DMA device will have the higher priority. Okay, so among all the requests, so the DMA request will give the higher priority when compared to the other peripherals. Okay, so you have a concept called a cycle stealing. So what is cycle stealing means? When the DMA controller tries to steal the memory cycles. Okay, so if you want to perform the read operation into by utilizing of 3 clock cycles, so when it steals the clock cycles, you're calling it as a cycle stealing. Okay, so you have an buffer, so which is used to store the data. If I want to get the data from your output device, it will be stored in the data buffer and it will be given to your memory or the processor. So we have a buffer which is going to act as an intermediate storage, and there is a possibility of block of transferring a block of data at a time, and whichever devices which is initiating a request, the DMA devices will have the higher priority. Okay, so next comes to a thing called bus arbitration. So the bus arbitration is nothing but, so the process of selecting a next bus master is called bus arbitration. Okay, so we know that what is the use of bus master. So if you want to initiate a data transfer, so if any devices which connected to your system, if you want to initiate a data transfer, first it have to access the bus master. If the bus master provides the rights, the particular device can transfer the data. Okay, so bus arbitration is nothing but the process of selecting a next bus master. So we'll be having a 2 arbitration, that is centralized arbitration and distributed arbitration. So in the centralized arbitration, so we have a process. So the processor is the device which is going to act as a bus master, and so the device wants to be the next bus master, will issue the bus request using their eventually initiate a signal called bus request, and the bus request will be taken to the processor. The processor will analyze the request and it will send the bus grant signal. So when the bus grant signal has been sent to from the processor, all the devices will be getting the bus grant signal, because if you see the block diagram, so this diagram has been connected in the form of a daisy chain. Okay, so what is the concept behind the daisy chain? So if the interrupt request has been initiated, it will be processed and the acknowledgement has been sent back. So when the acknowledgement reaches the devices, the device will process the acknowledgement. If it not belongs to it, it will make the acknowledgement to pass to the next device, because all the devices will connected in the form of daisy chain. So the bus grant signal, here the processor issues the bus grant and it will be reach the DMA controller 1. If the DMA controller 1 is not have the rights to become a bus master, now it will make the bus grant signal to pass through it, and then it will pass through a DMA controller 2. And if the DMA controller has been selected by the processor, this DMA controller 2 will become a bus master. Okay, this is called centralized arbitration. So the centralized arbitration is a simple thing where all the devices doesn't have a rights to select a bus master. You will be having a centralized device. The centralized device is responsible for selecting the next bus master. In a distributed arbitration, so all the devices which wants to become a bus master has a right or have the responsibility of selecting the next bus master. Here we doesn't have a centralized concept in the distributed arbitration. So all the devices have a responsibility of selecting the next bus master here. So this is a circuit diagram for a distributed arbitration. See here, if you see the diagram, so you will be having numbers like 0, 1, 0, 1, 1. Okay, so this is the unique ID where all the devices has. So if you want to become a bus master, what you have to do means, so you have to place your address, it is 0101 by using this line. and you will be get back your response. Okay, so if the particular device A has been selected as a bus master, you will be getting a response of the inverse of it. Okay, so see here 0, 0, 1, 1 is a device which is going to become a next bus master. So this is the ID of the device where it is going to become a next bus master in the distributed arbitration. So next is buses. Okay, so in the we know that what is bus. The bus is nothing but a communication link which is used to transfer your data and all kind of. We know that we have a control signals, we have a data signal, we have a control line, data line, and address line. So we have a 3 kinds of buses. But here we are going to discuss about. So what is the require of this bus? Okay, so if you see what is the main use of bus, it is the primary function of the bus is to provide a communication path for the data transfer, and each and every bus have its set of rules. Okay, so the set of rules have to be followed when the various devices connected to the bus. And we know that we have a 3 types of bus line, that is data, address, and controls. And the control signals will be carried the timing information. And here, if you want to transfer the information to the other devices, I have a bus master. That is, you have a 2 concepts over here. One is the bus master, who is an initiator, and it is a slave, that is a target device. Okay, so the device which initiates the transmission, you're calling it as a master, and the device wants to be response is nothing but a slave, or you can call it as a target. Okay, so you will be having 2 kinds of bus, that is a synchronous bus and asynchronous bus. So in the synchronous bus, actually we will be having a fixed timing signal, that is we will be having a fixed clock cycle. So within this clock cycles, the entire operation needs to be complete. Okay, see here in the synchronous bus, so you have a bus clock, that is you have only 1 clock cycle. This is a fixed cycle, it has been done. And you have an master. So who's the master? The master who initiated the transaction, that is who initiate the data transfer is a master, and who wants to respond is a slave. So the master is going to place the address when the clock has been initiated. So it will take some little time to place the address, it is TAM, and you have a data. Once the address has been placed, so depends on the address, the data will be retrieved, and it will be it has been happened in the 2nd clock cycle. Okay, so and it has been seen by the slave. Okay, and the data has been retrieved by the slave. So this slave is nothing but an output device, and the master is nothing but the processor which is going to send the data to the slave, and based on the address it retrieves the data, and the data has been used by the slave devices within this particular fixed clock cycle. So synchronous bus is nothing but the fixed clock cycles you have. An asynchronous bus is nothing but a handshake signal, that is you have an handshake mechanism between your master and slave before starting your data transmission. So the master have to check the availability of the slave. So if the handshake mechanism has been happened properly, so you can go for the next transmission. See in the first for example, in the cycle T0, the first clock cycle where your address has been kept, and then in that time T1 the master is ready, and in time T2 the slave is ready. So once the master is ready, it has kept the data in the clock cycle that is timing T2, and it takes around T2, T3, and T4 to transmit the data, and the process has been ends with the time T5. Okay, so this is the asynchronous bus, whereas the handshaking protocol has been used for your input-output operation. So you have to check for the master. If the master is ready, and you have to place the data, and the slave is ready to accept the data, so the process gets completed within the utilization of T5. That is here we doesn't have any fixed clock cycles. So it depends on the operation, the timing, the time availability, or the time utilization differs. So next is an interface circuit. So I have told you that in the interface circuits we have studied about address, data registers, and control circuits and all. And we have under your interface circuits, we have two ports, that is parallel port and serial port. So the parallel port, which transfers the data in form of bits, it is going to transfer the data in whether in of 8-bit at a time or 16-bit at a time. That is, you're going to transfer the bits parallelly, and for this parallel ports will be used mainly for faster communications. Okay, so this is the example which have been given how the keyboard is going to interact with the processor. So if the keyboard has been pressed, that is if any key has been pressed, so it uses an encoder. Okay, so what is the use of encoder? Whatever key which has been pressed, which is of an it is kind of signal, right? So this signal has been converted to an ASCII code, and the data will be given to the interface, that is input interface. We know that we have data in an SIN registers, and the data will be available in SIN, and it will be taken by the processor using the data, and the address will be given to the interfaces using address line. Will be having read and write, and if it is an asynchronous, we'll be having master ready and slave ready. We have a different lines for sending the master ready signal and slave ready signal. So this is the example for your keyboard. Okay, so keyboard access, and how this is the example for the parallel port, that is how the data has been transferred to the printer, that is an output device. And next in the serial port, so the serial port you can able to transmit only 1 bit at a time. Okay, so it's not like a parallel port. In the parallel port we can able to transmit more than 1 bit at a time, but in a serial port the transmission of bits can be happen only 1 bit at a time. And this is the block diagram for a serial port. So here you will be having an input shift registers, data in and data out. So here the transformation of your parallel port to the serial port will be done with the help of shift registers. Okay, so here you will be having an input shift register and output shift registers, right? So this shift register will be used for the transformation of parallel port to the serial port, because the parallel port can able to access more than 1 bit at a time, but the serial port can able to access only 1 bit at a time. Okay, so if you have a shift register, so the transformation of parallel port to the serial port or serial port to the parallel port can be happened easily. So next is your standard input output interface. So here in the standard output interface, okay, so we are going to discuss about peripheral component interconnect, that is PCI. So here in the PCI, see here, this is a block diagram for the PCI. Here you can find a component called PCI bridge. Okay, so what is the use of PCI bridge means? Because the whole, you have a different components like processor, memory. So all this component has been connected to a processor bus. Okay, so each and every bus will be having a different standard. Okay, so if you have an PCI, it is a peripheral component interconnect. So where you can connect the other devices like disk, printer, and your you have an Ethernet interface. So if these devices wants to connect to the processor bus, so the standards of these devices will not be support the processor bus. Okay, so you need an intermediate over here, that is called PCI bridge, which will help you to convert these standards to the as per the processor bus. Okay, so actually we'll be having an different data transfer signals in the PCI bus. So first is you will be having a clock. Okay, this is a signal where this is a clock which has been set for your PCI transaction, that is PCI signals. Next you will be having a frame. Okay, so what is a frame in the sense, as I told you in the previous slide, so the device once who initiated a transfer is called master, and the device which wants to respond for the particular device is being treated as a slave. Okay, so the master will be called it as an initiator and the slave will be called it as a target. Okay, so when the initiator or when the master initiated your operation, so the time has been fixed. So it will indicate this is the time duration which have to take to complete this particular transaction. So it will be set by a signal called frame signal. So this frame signal which will indicate the duration of transaction, And here in your PCI bus, so we have an important concept in your PCI. So what it means, so if the master plays the address, okay, so once the address which has been once the address has been seen by your target device, so the same address line will be used to transfer its data. That is the AD signal. So AD signal is nothing but it is a combination of address and data. So here we doesn't have two different lines. So before we will be having a control line, address line and data line. So if you want to transfer the address, it will be done by your address line, and if you want to transfer the data, which will be done by your data line. Okay, so here, so once you have been placed your address, your address will be just it will be accessed by your slave, and after giving the data, the same address line will be used. That is the 32 address and data lines will be used, and it will be it can be increased to 64. So the next signal you will be having is command and byte enable signal. Okay, so this is the signal which is used to transfer the command. And next you will be having an IRDY, that is the initiator ready, and TRDY is the target ready. Okay, so IRDY is the initiator and target ready, and next is a device select, that is DV self is nothing but a device select. So which is the response from the device indicating that it has recognized its address. So once the address has been placed using the address line, the device recognizes its address and it is ready for the data transmission will be indicated by the device select. Okay, so once the devices get selected, and you're going to initialize the device select using a signal called IDSL. Okay, so this is the that is the read operation on the PCI bus. So you will be having a 7 clock signals. That is within the 7 clock signals, the entire operation is going to complete. See here, you have a different signals like frame. So what is the use of frame? So you are going to fix the duration. So what is the duration you have been fixed? So you have fixed within the 7 clock cycles, the read operation have to be complete by using a PCI bus. And in the ADI is nothing but a line which is used to place your address. Once the address has been recognized for the particular device, it is going to place the data. So how many data it is going to get placed? It is going to place 4 bytes of data. Okay, so once the address is recognized and the data has been placed, so you are enabling the command bit and you are enabling the byte enable bit to retrieve the data from your data line. And see here, so in the second clock cycle, as the device is placed the address, the initiator, that is the initiator ready has been, the signal has been raised. Okay, so which means that the master placed the address. Once the address has been placed, which will be received by your target, that is the slave. The slave, what it does, it will seize the address. It depends on the address, the data will be retrieved and the data was placed on your data bus. And once the data has been placed, your device select, that is a particular device has been selected for a device transmission, and this 4 byte of data has been transferred. Okay, so this is the USB tree structure. So in the exam point of view, so the most important question is your what is the direct memory access, and then interrupt, that is interrupts, enabling and disabling the interrupt, polar and vector mechanisms. All these are the important question. This is the USB structures. So where you have a host computer and you have a different input output devices connected to the USB. Okay, so and host computer can be a root, and you will be having a different hubs, and the many devices can be connected to hubs, and you will be having an high speed connection and you will be having a low speed connection, because the data transmission there, that is the transmission speed get varies. So depends on the transmission speed, we are going to make the availability of high speed bus or low speed bus. And how we will be having a different protocols for your PCI bus. The USB also has a different set of protocols where all the information we are going to transfer to the USB is being transferred in form of packets. Okay, so each packet will be consist of 1 or more bytes of information, and the information transferred on USB will be divided into 2 categories, that is control and data. So you have a control packets and data packets. So this control packets, which will be based on to initiate a data transfer and how to get the acknowledgement from the other devices, and the data packets where your original data has been resigned. So this is a packet format you have. See here, you will be having the packet identifier field. You will be having 0, 1, 2, 3, and it will be keeps on repeating. That is 0 to 3 will be repeating, and you have an packet for in and out operation. So you have a packet ID and you have an address and you have an end of packet, and you will be having an CRC16. It is an error check mechanism which will be added to each packet. And you will be having an data packet, so where you will original data get resides, and each and every packet will have its own identifier. That is, a PID is nothing but a packet identifier. And in your output transfer, see here, you will be having a host and you will be having a input output devices. The host is generating a token and it will reaches the interconnecting device. It is an hub, and the data 0 has been transferred, and it receives the acknowledgement, and the data 2 will be getting transferred. And after the hub receives the data, it will be, the hub is going to act as an interconnecting device. Whatever data which will be got from the host will be directed to the input output device. That is data 0 received by the hub. After sending the acknowledgement from the hub, the token has been sent to your input output device, and data 0 has been sent to your input output device. Again, you are getting the acknowledgement from an input output device to the hub, which means that the token and the data has been received properly. Okay, and for a data, second data, as same as the first cycle. So you have initiated the token and you have sent a second data. It reaches the hub, and after sending the acknowledgement, you are being started transmitting to the input output device, and you are getting the acknowledgement to the hub. So the acknowledgement which received from input output devices to the hub, which means that the data has been reached properly to the devices. Any questions? Any questions? Okay, so thank you for attending today's session actually. So today we have covered module 1 and module 2, and tomorrow we will be covering of module 3 and module 5. Okay, so module 3 will be started in the morning. Actually, that is the first module we are going to cover. We are going to start by 9:30. Everyone please try to join by 9:30 because the portion is vast and we can't complete within 4 hours, because tomorrow also we have to cover up 2 modules. So try to join in time. So everyone be assemble at 9:30 and inform your friends also to join and attend the session. Thank you.